Welcome to the Forgotten Covenant, where ancient lands awaken and thoughts find calm. Tonight we journey into a frozen world reminiscent of the age of mammoths and saber-toothed hunters. Let us know where you're watching from and what time it is for you. A glacial period is a long-lasting interval in Earth's history, marked by a deep, global cooling that spreads massive ice sheets across continents. Unlike a regular winter or seasonal chill that lasts only a few months and affects limited regions, a glaciation can endure thousands or even millions of years, radically reshaping climate, geography, and ecosystems. During such times, average temperatures drop noticeably, and ice pushes far beyond the poles into mid-latitudes, carving new landforms. The crucial difference between a glaciation and ordinary cold spells lies in scale and duration. Seasonal winters are brief, driven by Earth's orbit and axial tilt, producing predictable yearly cycles of cold and warmth. Glaciations, however, bring a sustained global chill, with ice sheets persisting for millennia, occasionally interrupted by warmer interglacial intervals. In those interglacials, the ice extent shrinks, yet the alternating pattern of glacial and interglacial phases defines the ice ages. Glacial cycles are guided by changes in Earth's orbit, Milankovitch cycles, that alter the amount and distribution of solar energy reaching the planet. Over time, these variations, together with atmospheric composition, volcanic activity, and ocean currents, drive the advance or retreat of ice sheets. Understanding the contrast between a single winter and an ice age highlights the immense power of Earth's climate system. While a winter may bring snow to a region, an ice age reshapes entire continents, creates new relief, and steers the evolution of life over thousands of years. The most recent ice age, known as the Quaternary glaciation, began about 2.5 million years ago and continues today, though the ice sheets have waxed and waned. Its last major advance, the last glacial maximum, peaked roughly 20,000 years ago. During that era, massive ice sheets blanketed large parts of North America, Northern Europe, and Asia, reshaping the land and its ecosystems. The shift from glacial to interglacial conditions was driven by changes in Earth's orbit, axial tilt, and precession, together known as Milankovitch cycles. These cycles altered how much solar energy reached different regions, setting up a rhythmic pattern of cooling and warming. The last glacial period ended roughly 11,000 years ago, giving way to the current interglacial, the Holocene. Its relatively stable climate allowed human societies to develop. Throughout the whole span, the borders between glacial and interglacial phases were marked by dramatic environmental changes. Advancing ice sheets, sea level drops, then retreats, sea level rises, and sweeping shifts in plant and animal life. In glacial phases, ice expanded and locked away huge volumes of water, causing sea levels to fall. In interglacials, ice receded, sea levels rose, and global temperatures increased. This alternation sculpted the planet's surface, redirected ocean currents, and steered the evolution of species. Understanding these key milestones helps us grasp the ever-changing nature of Earth's climate system. Precise dating of the cycles lets scientists rebuild past climates and better predict the forces still shaping today's weather. A glacial epoch is defined by sustained, widespread cooling, global temperatures dropping several degrees Celsius below interglacial averages, and by continental ice sheets covering vast territories. This cooling stems from the interplay of orbital parameters that control sunlight distribution, creating cold spells that can last from tens to hundreds of thousands of years. Lower temperatures cause polar ice to spread far beyond its usual limits, increasing Earth's albedo and reflecting more sunlight, which reinforces the chill. Growing ice carves deep valleys and reshapes the landscape, while vegetation retreats, turning once green areas into tundra or desert-like zones. Ecosystems adapt to harsh, resource-scarce conditions, and precipitation patterns shift. Some regions receive more snow that feeds the ice sheets, while others become increasingly dry. Cold temperatures combined with altered precipitation patterns carve a landscape of deep fjords, U-shaped valleys, and moraines. Moraines mark the edges where glaciers have retreated, and studying these features gives vital clues about past ice ages. Researchers piece together the Earth's glacial history by examining the geological record left on the planet's surface. One of the chief sources of information is glacial sediment, thick layers of till, gravel, and layered deposits left by advancing and retreating ice. These deposits, often found in moraines and outwash plains, serve as tangible markers of ancient glacial activity. By analyzing their composition, location, and structure, scientists can reconstruct the extent and timing of ice sheets over millennia. Landforms sculpted by glacial erosion, U-shaped valleys, fjords, and drumlins, also reveal the direction, strength, and reach of past ice flows. Large boulders carried far from their source, rocks further illustrate glacier pathways and dynamics. Sediments accumulated in lakes and oceans add another layer of evidence. Cores extracted from these deposits contain sequential layers of pollen, ash, and other materials that record environmental changes over time. Isotopic analysis, especially of oxygen isotopes in ice and marine sediments, allows researchers to track shifts in global temperature and ice volume. The ratio of these isotopes changes as ice sheets grow and melt, providing a precise clock for glacial cycles. Fossil remains of plants and animals complement the physical data, showing how ecosystems responded to cooling events. Combined with radiometric techniques such as radiocarbon dating of organic matter and uranium-lead dating of minerals, these diverse records enable scientists to build an accurate chronology of ancient glaciations. Integrating geological, chemical, and biological evidence, scientists reconstruct the Earth's glacial past and uncover patterns of climate change that have shaped the planet's surface for countless thousands of years. This comprehensive approach clarifies the alternating glacial and interglacial periods within each ice age, climatic phases driven by complex interactions among Earth's orbit, atmospheric composition, and ocean currents. During glacial periods, massive ice sheets spread far beyond their modern limits, covering large portions of North America, Europe, and Asia, sometimes reaching heights of several hundred meters and dramatically reshaping the terrain. During glacial times, the climate turns noticeably colder, often by a few degrees Celsius. A spread-out ice cover reflects incoming sunlight, strengthening the cooling. This is the albedo feedback. The extensive ice also blocks moisture transport, so some regions receive less precipitation, which helps the ice sheet keep growing. Between glaciations, the climate warms. Ice sheets shrink, uncovering lands that were hidden under ice. Temperatures can rise by 4 to 8 degrees Celsius compared to glacial phases, creating better conditions for forests, steppes, and diverse ecosystems. The melt adds a huge amount of water to the oceans, raising sea level by up to about 120 meters above the glacial maximum. Coastal plains become flooded, continental outlines change, new habitats appear, and ocean circulation is reshaped. These shifts are driven partly by modest variations in Earth's orbit, known as Milankovitch cycles, which alter how much solar energy reaches the planet. Changes in greenhouse gas concentrations, especially carbon dioxide and methane, also modulate the climate, amplifying cooling during glacial periods and warming during interglacials. Such cycles repeat over tens to hundreds of thousands of years, carving the planet's climate history and steering the evolution of the biosphere. The contrast between glacial and interglacial periods shows how sensitive Earth's climate system is to a mix of internal and external forces. This sensitivity reshapes not only the land, but also global climate patterns and sea level changes that will be discussed next. Fresh water from melting ice can weaken or even divert major currents like the Gulf Stream, bringing regional cold spells or warm periods. These linked processes form a moving climate system that swings between cold and warm phases, shaping Earth's natural history. Glacial epochs and sea level changes are just one piece of a far richer picture. To see the whole story, we must grasp what times the ice ages start and how fierce they become. And that hinges on subtle yet powerful shifts in Earth's orbit. These orbital shifts, known as Milankovitch cycles, drive the timing and intensity of glaciations. They have three main parts. First, roughly every 100,000 years, the orbit's shape, its eccentricity, changes from more circular to more elongated. The more stretched the orbit, the bigger the gap between the closest point to the Sun, perihelion, and the farthest, aphelion, sharpening seasonal contrasts. Second, about every 41,000 years, the tilt of Earth's axis varies. A larger tilt makes summers hotter and winters colder, which can either foster ice growth or melt it, depending on the season. Third, the axis wobbles, a precession cycle lasting about 23,000 years, shifting the timing of the seasons relative to Earth's position on its orbit and altering how sunlight is spread across latitudes. These factors don't act alone. Together, they reshape the pattern of solar radiation reaching the planet. When the northern hemisphere experiences cooler summers, ice sheets can expand, sparking or intensifying a glacial period. When summer insolation rises, ice retreats and a warmer interglacial begins. This interplay explains the rhythmic rhythm of ice ages throughout Earth's history. Understanding how orbital changes steer glacial cycles reveals the fragile balance of the planet's climate system. It gives us a deep context for today's climate shifts, showing that the same intertwined forces that drove past ice ages still influence the modern climate and help scientists forecast future trends. Sharp swings in global temperature and ice cover during past ice ages demonstrate that climate can shift rapidly, reminding us that today's warming is part of a broad, moving system rather than an isolated blip. Ice Age research underlines the power of feedback loops. When snow and ice spread, they reflect more sunlight, deepening the cold, a process known as the albedo feedback. In the warm interglacial phases, shrinking ice lets the planet absorb more solar energy, further accelerating heating. Seeing how these feedbacks operated in Earth's past helps scientists anticipate how today's greenhouse gas emissions might trigger similar amplifications. It also reveals how finely balanced the climate system is. Tiny nudges can produce massive outcomes.
Understanding the natural rhythm of glacial cycles lets us separate human-driven changes from purely natural swings, a distinction essential for sound climate policy. Glacial periods arise from a tangled web of Earth's orbital dance, solar radiation, atmospheric makeup, and ocean currents. Studying the onset and transition phases of these epochs sharpens our ability to spot early warning signs of modern tipping points. In essence, ice ages act as a mirror that reflects both the resilience and the fragility of Earth's climate, showing the scale of natural variability and reminding us of our responsibility to the planet. The planet's climate history is tightly linked to cosmic rhythms.
The primary drivers of long-term climate shifts are astronomical factors that subtly but continuously alter Earth's position relative to the Sun. These influences are encapsulated in three parameters: orbital eccentricity, axial tilt, and precession, that together form the Milankovitch cycles, operating on timeframes from tens to hundreds of thousands of years. Eccentricity describes how stretched Earth's orbit is. When the orbit becomes more elliptical, the distance between Earth and the Sun varies more dramatically over a year, changing the intensity of received solar radiation. These variations tweak seasonal contrasts, playing a decisive role in initiating glacial and interglacial periods. Eccentricity shifts slowly, cycling roughly every 100,000 years, but its impact grows when combined with the other orbital motions. Axial tilt swings between about 22.1 and 24.5 degrees over a cycle of roughly 41,000 years. A greater tilt heightens seasonal differences, allowing ice sheets to expand during colder times. A smaller tilt softens seasons, encouraging ice melt and warming. Precession, the gradual wobble of Earth's rotation axis, completes a cycle in about 26,000 years, further modulating the timing of seasons and the distribution of solar energy. The tilt, shape, and wobble of Earth's orbit shift the seasons relative to the planet's position around the Sun, changing how solar energy is shared between hemispheres. Together with eccentricity and axial tilt, precession can strengthen or weaken seasonal differences, making it a central driver of glacial cycles. These orbital factors do not act alone. Their long-term cyclic interaction controls insolation, the amount of solar radiation reaching the surface. This celestial dance sets the timing and intensity of ice ages, imposing the planet's major climate rhythms. Milankovitch cycles provide the basic tempo for Earth's long-term climate variability. They involve gradual changes in orbital eccentricity, axial tilt, and precession, each operating on timescales from roughly 40 to 10,000 years. Eccentricity describes how the Earth's path around the Sun varies from nearly circular to more elliptical, influencing the total solar energy received. When the orbit becomes more stretched, the contrast between perihelion and aphelion grows, sharpening seasonal contrasts, especially at high latitudes. Axial tilt oscillates between about 22.1 and 24.5 degrees, setting the severity of seasons. A larger tilt makes summers hotter and winters colder, while a smaller tilt yields milder conditions. Precession, the slow wobble of Earth's rotation axis, shifts the timing of solstices and equinoxes relative to the orbit, further modifying seasonal contrasts between hemispheres. When eccentricity, tilt, and precession align so that summer insolation in high northern latitudes drops, ice sheets can advance, triggering glaciation. Conversely, periods of enhanced summer insolation promote ice sheet melt and mark the end of glacial periods. Orbital variations alone do not create ice ages. They merely set the background energy balance.
Feedbacks involving atmospheric composition, especially carbon dioxide and methane, can greatly amplify or suppress climate responses. Greenhouse gases act as active regulators, participating in feedback loops that intensify or moderate temperature changes, thereby influencing the rise and retreat of massive ice sheets. As ice sheets grow, they raise Earth's reflectivity, sending more sunlight back into space and cooling the planet. Cold temperatures usually coincide with lower carbon dioxide levels because chilly oceans take up less CO2, and changes in biological productivity cut greenhouse gas concentrations even further. This creates a reinforcing loop that keeps glacial conditions alive. Glacial periods end when greenhouse gases gradually build up, trapping outgoing infrared radiation, warming the world, and forcing the ice sheets to retreat. The natural ups and downs of these gases stem from a mix of physical, biological, and geological forces, shifts in ocean circulation, changes in vegetation cover, and volcanic activity. Together, they dictate how quickly Earth moves from a glacial to an interglacial state. Orbital variations set the stage for ice ages, while greenhouse gases amplify the impact and decide each period's harshness and length. Their atmospheric concentration can either lock in cooling or speed up warming, acting as an internal climate regulator. Human actions already disturb this natural balance, threatening future climate stability. Volcanoes and the aerosols they release also play a crucial role. Explosive eruptions fling ash and sulfur dioxide into the stratosphere, where the particles reflect sunlight and trigger short-term cooling, known as volcanic cooling.
If an eruption occurs during a sensitive phase of the climate cycle, it can launch or strengthen glacial conditions. Sulfate aerosols linger for months or years, maintaining lower global temperatures. During glacial transitions, heightened volcanic activity can prolong cold spells, encouraging ice growth, while the cessation of large eruptions reduces aerosol levels, allowing warming to resume and potentially ending an ice age. These volcanic effects intertwine with greenhouse gas levels and orbital changes, often aligning with natural cooling cycles and highlighting the complex feedbacks that drive Earth's climate. Volcanic aerosols play a surprisingly strong role in pushing the climate toward glaciation, showing how brief external events can steer long-term climate patterns. While Earth's orbital parameters and atmospheric composition set the baseline, individual eruptions can act as catalysts that tip the system toward an ice age or an interglacial period. Recognizing these links deepens our appreciation of the planet's climatic complexity and the delicate balance that has persisted for millennia. When we examine the drivers of glacial cycles, ocean currents and heat distribution emerge as equally crucial. Surface currents ferry warm water from the equator toward high latitudes, while deep water flows return cold water poleward. This massive conveyor reshapes temperatures worldwide, often nudging the climate toward either further ice buildup or a warmer interglacial state. During glaciations, alterations in the paths of major currents, such as the Gulf Stream or the thermohaline circulation, can dramatically reduce the supply of warmth to polar regions. A weakened or disrupted thermohaline system transports less heat to the poles, fostering the expansion of ice sheets. Conversely, changes that boost warm water influx can stall or slow glaciation. The layout of continents and the shape of the sea floor tightly control how currents move. When sea level falls during an ice age, continental shelves become exposed, rerouting currents and often intensifying cooling. Such rerouting can trigger feedback loops. Expanding ice sheets raise the planet's albedo, reflecting more solar radiation and prompting further cooling. Stronger polar sea ice then acts as an insulating lid, limiting heat exchange between ocean and atmosphere, and reinforcing low temperatures. Cooling of the ocean surface also alters atmospheric moisture capacity and precipitation patterns. These shifts can either support the growth of ice sheets or, through increased cloud cover, produce localized warming. The interplay between oceanic heat transport and these feedbacks underscores their central role in initiating and maintaining glacial cycles. Even modest adjustments to ocean pathways, whether driven by tectonic shifts or orbital variations, can cascade into major climate transformations that set the stage for the next advance or retreat of ice. Beyond moving heat, ocean currents help generate feedback mechanisms that amplify or dampen climatic swings during glacial periods. One of the most powerful amplifiers is the albedo effect. As ice sheets spread, the Earth's reflectivity rises, reducing solar absorption and further cooling the climate. These self-reinforcing loops are key to the strength and duration of glacial-interglacial oscillations. As ice sheets expand, they reflect more sunlight, which deepens the cold and allows even more ice to accumulate. When the ice retreats, dark land or ocean surfaces are exposed, absorbing heat and accelerating warming. This negative feedback slows the rapid temperature swing. Greenhouse gases, mainly carbon dioxide and methane, are key regulators of this cycle. During cold periods, these gases become trapped in ice and ocean sediments, reducing their atmospheric concentration and reinforcing the chill. In warm phases, they are released from natural stores, boosting the greenhouse effect and hastening temperature rise. The continual exchange creates a fragile balance that influences both the advance and retreat of glaciers. Plants also play a role. Growing ice sheets shrink terrestrial vegetation, lowering the planet's capacity to pull carbon dioxide from the air. Less plant growth means higher atmospheric CO2, which further intensifies cooling. Conversely, when glaciers melt, vegetation expands, drawing down CO2 and moderating warming. Oceanic feedbacks, especially changes in thermohaline circulation, redistribute heat and carbon throughout the climate system. During glacial times, shifts in deep water currents can either amplify cold by moving frigid water toward the poles, or soften it by channeling more tropical heat northward. Continental arrangement is another crucial factor. Plate tectonics reshapes the layout of land and sea, altering atmospheric and oceanic circulation, and thus global climate stability. When continents sit near the poles, extensive land masses accumulate snow, fostering the growth of ice sheets, as happened in past ice ages. If continents drift toward the equator, a warmer tropical climate prevails, discouraging ice formation. The shape of the continents also steers ocean currents. Opening or closing sea passages, such as the link between the Atlantic and Pacific, can dramatically reroute heat transport. For example, the emergence of a large land bridge like the Panamanian Isthmus redirected currents, funneling colder water into higher latitudes and supporting extensive ice sheets. Massive high-latitude land masses can also deflect jet streams and storm tracks, prolonging cold conditions over continents and aiding glaciation. Together, these intertwined feedbacks, reflectivity of ice, greenhouse gas cycles, vegetation changes, ocean circulation, and continental positioning, govern the rise and fall of Earth's ice sheets, revealing how interconnected processes have amplified or dampened climate swings throughout the planet's deep history. Throughout Earth's history, the drift of continents has repeatedly lined up with changes in the planet's orbit, giving glacial periods a cyclical rhythm. As land masses move, They reroute heat and moisture, setting the stage for ice sheets to grow or shrink. Over millions of years, these tectonic shifts interacted with other climate drivers, forming feedback loops that drove long-term climate swings. This deep link between continental layout and climate prompts the question: can extraterrestrial forces also spark glaciations? Astronomical factors, collectively called Milankovitch cycles, alter Earth's orbital shape, eccentricity, axial tilt, and precession. Each adjustment reshapes solar radiation's distribution, gradually nudging the climate toward colder or warmer states. Higher eccentricity strengthens seasonal contrasts, especially cooling northern summers. A smaller tilt flattens temperature differences. Precession shifts the timing of seasons relative to Earth's orbital position. Together, these parameters control the amount of solar energy reaching high latitudes, where ice is most sensitive. When summer insolation in the north drops enough, snow persists year-round, accumulating into vast ice sheets that can blanket continents and usher in a new ice age. Understanding these cosmic influences shows how external forces can upset Earth's fragile climate balance and trigger major glaciations. Glaciers themselves are massive, slow-moving rivers of ice, formed from compacted snow that, over many years, exceeds melt and evaporation, gradually turning into dense crystalline ice. The buildup of ice begins where the climate stays cold enough that snow does not melt completely, typically in high latitudes or mountainous regions. As snow layers grow, their weight compresses the lower layers, expelling air and increasing density. Over decades or centuries, these compacted layers fuse into solid ice. This transformation is gradual, driven by gravity, pressure, and temperature. Once a glacier reaches a critical mass, it slowly spreads outward and downhill, carving valleys and reshaping the terrain beneath it. Glacier formation is tightly linked to the climate of glacial periods. When global temperatures drop, snow persists longer each year, allowing glaciers to thicken and expand. Continuous snowfall adds to their thickness and area, and individual glaciers often merge into vast ice sheets that can cover hundreds of thousands of square kilometers. Their growth hinges on a delicate balance between snow accumulation on the surface and melting or sublimation at the margins. If accumulation exceeds losses, the glacier advances onto new ground. If melt outpaces snowfall, it retreats. During the ice ages, prolonged cold tipped this balance toward growth, creating massive ice sheets that covered large portions of continents. Understanding how these ice sheets formed reveals the mechanisms of their growth and movement, which in turn shaped the broader landscape. When such sheets, like the Laurentide and Eurasian ice sheets, expanded, they dramatically altered the Earth's surface. In periods of intense cooling, usually coinciding with glacial maxima, abundant snowfall accumulates over vast land areas. The added snow outweighs the ice that melts in warmer seasons, increasing the overall ice mass. Continuous accumulation causes the ice sheet to spread, filling valleys and covering extensive continental regions. The development of the sheet depends on the same balance between gain and loss. Low temperatures and moisture carried by polar or westerly winds bring fresh snowfall, which, under the pressure of overlying layers, gradually compacts into solid ice, a process called fernification. Over decades or centuries, granular snow becomes a continuous ice mass. As the sheet thickens, pressure at its base rises, and the ice begins to flow outward under its own weight, following the underlying topography.
Gravity is the primary driver, causing the ice to slide, deform, and slowly remodel the landscape. Climatic fluctuations play a crucial role during expansion phases. Colder intervals slow melting, while changes in sea level and ocean currents affect moisture supply to the ice sheet's edges, influencing further growth. The size of an ice sheet also depends on available moisture, the shape of the land, and mountain ranges that channel ice flow and direct snowfall. For example, in the last glacial period, the Laurentide ice sheet rapidly expanded, covering much of North America thanks to a combination of low temperatures and intensified snowfall at high latitudes. The Eurasian ice sheet grew in the same way, fed by heavy snowfall over northern Europe and Siberia, intensified by cold Arctic air masses. Its buildup illustrated the dynamic links between climate, geography, and atmospheric circulation. Expanding ice sheets reshaped the Earth's surface and profoundly affected global climate and sea level during the glacial age. It is useful to distinguish the three main types of ice masses: ice sheets, ice caps, and individual glaciers. Ice sheets are the largest, covering thousands of square kilometers and holding colossal volumes of ice. Today, they exist mainly in Greenland and Antarctica. Their sheer size allows them to blanket entire continental regions, and their weight and movement can remodel landscapes, alter sea level, and influence the planet's climate system. Ice caps are smaller, typically dome-shaped bodies that drape high-latitude or mountainous areas, usually occupying less than 50,000 square kilometers. Unlike ice sheets, they have a more localized impact, shaping the terrain directly beneath them without reshaping whole continents. Individual glaciers are the most mobile and vary widely in size, from modest mountain streams to extensive valley glaciers. They often originate from ice caps or sheets and flow downhill under gravity, carving valleys, fjords, and other landforms. Their erosion and deposition continually modify the surrounding terrain, creating moraines, drumlin fields, and other features. Glacial erosion mainly occurs through plucking and abrasion. Meltwater seeps into cracks, refreezes, and loosens blocks of bedrock, which the glacier then lifts away, producing jagged or rounded landforms.
Simultaneously, embedded rock fragments grind against the substrate, polishing and scouring it. This dual action of erosion and sediment accumulation underlies the powerful role glaciers have played in reshaping Earth's landscape throughout its history. Finely ground rock fragments created by a glacier's grinding action carve smooth grooves and polished surfaces. These marks preserve evidence of ice movement for a long time, indicating the direction and strength of ancient flows. Deposition begins when a glacier loses energy and its carried material settles. During advance or retreat, the glacier drops a wide range of sediments, from thin silt to large boulders. Lateral moraines along the glacier's sides, terminal moraines at its snout, and medial moraines formed within the ice are the most visible results. These deposits not only outline former glacier margins, but also shape the future landscape, producing fertile soils and sharp relief boundaries. The combined action of erosion and deposition generates many landforms, U-shaped valleys, fjords, drumlins, each bearing the imprint of ice motion. By repeatedly advancing and receding, glaciers carve the terrain, expose bedrock, and leave behind sediments that continue to influence the area long after the ice has vanished. Understanding these processes shows how glaciers have continuously reshaped Earth's surface, leaving a landscape rich in history and geological complexity. Glacier movement stems from a mix of physical mechanisms that let massive ice bodies travel great distances over time. The core driver is plastic deformation. The weight of accumulated snow compresses lower layers, turning ice into a viscous material that slowly deforms and flows.
especially in deeper, warmer sections where pressure and temperature ease deformation. Surface melting also plays a key role. Meltwater infiltrates cracks and basal cavities, reaches the bed, and lubricates the ice-rock interface, reducing friction and allowing the glacier to slide more easily. This basal sliding often triggers rapid advances or sudden accelerations, particularly in temperate glaciers where melting is pronounced. Flow behavior also depends on glacier shape and underlying topography. Steep slopes speed up movement, while gentle bedrock creates zones of compression and tension within the ice.
Encountering obstacles or changes in terrain produces crevices, which not only appear on the surface, but also signal internal stresses, revealing how the glacier reacts to forces from below and outside influences. Climate conditions, temperature, snowfall, meltwater volume affect accumulation and ablation rates, altering the glacier's mass balance. Shifts in these factors can change both the speed and direction of glacier motion. The delicate balance among internal deformation, basal sliding, and external forces gives glaciers their dynamic, ever-changing nature, making them true giants shaped by physics and environment. To understand past ice sheets, scientists blend new measurement techniques with modeling, using both direct observations and indirect geological data. Because ancient ice can't be measured directly, they rely on a suite of methods to reconstruct its former shape. The chief approach is to study landforms created by glaciers, U-shaped valleys, fjords, and drumlins that record the old ice cover. From these features, researchers map the extent of the sheets at different times. Sedimentary clues also help. Unsorted glacial till marks where ice once rested, while layered deposits show how the margin moved. Isotope analysis of marine and lake sediments refines the picture. The ratio of oxygen isotopes in deep-sea cores indicates global ice volume. During glacial periods, when ice sheets lock up water, lighter isotopes remain in the ocean, leaving a trace that, together with debris from glacial erosion, lets scientists estimate the amount of land ice. Modern geophysical tools, seismic surveys, and gravity measurements reveal thickness and internal structure of surviving ice caps, and these data feed computer models that reconstruct larger, now gone ice sheets. The models combine all data sources and simulate growth and retreat over time, accounting for climate, topography, and ice-rock interactions. When calibrated with geological evidence, they give detailed reconstructions of ice sheet development, total volume, and impact on sea level. This interdisciplinary approach, linking landscape analysis, sedimentology, geophysical surveys, and numerical modeling, allows researchers to piece together the changing history of Earth's ice sheets. Continuous integration of new data deepens our understanding of how these ice giants expanded and shrank over millennia, shaping climate and landscapes long before written history. The geological record preserves the traces of ancient glaciers, providing crucial information about their former size and movement. One of the strongest pieces of evidence is glacial striations, straight scratches cut into bedrock by moving ice. These deep grooves show flow direction and the immense pressure exerted over thousands of years, often accompanied by polished surfaces that record abrasive action by debris carried in the ice. In addition to rock marks, scientists examine characteristic landforms produced by glacial activity. Moraines, ridges of unsorted material deposited at glacier margins, mark former ice boundaries. End moraines indicate the farthest advance of a glacier at its maximum, while lateral moraines outline its sides and trace former limits.
These features can stretch for hundreds of kilometers, preserving a visual record of ice sheet fluctuations. Subglacial lakes and sediments also supply important clues. When glaciers melt and retreat, they leave thin layers of fine-grained deposits, known as varves, along with yearly bands of silt and clay that record seasonal shifts. Counting these varves lets scientists track how the size of ice sheets changed over thousands of years. Large rocks dropped by melting ice, drop stones, mark the paths of icebergs that broke off from the shelves and drifted into the ocean. The presence of glacial debris in marine sediments further confirms the extent of ancient ice cover. As icebergs break apart, they carry fragments of rock. When the ice melts, these fragments settle on the seafloor, creating distinct layers that help build the timeline of glacial advance and retreat. By combining evidence from bedrock, landforms, sediments, and debris, researchers reconstruct a detailed picture of how ice sheets grew and shrank throughout Earth's climate history, revealing the dynamic nature of ice during the glacial periods. Ice sheets, massive expanses of continental ice, strongly influence global sea level. When they accumulate, they lock away vast amounts of fresh water, lowering sea level by roughly 120 meters at glacial peaks. This drop exposed continental shelves and formed land bridges that reshaped coastlines and migration routes for humans and animals. As the climate warms and ice sheets melt, the stored water returns to the oceans, causing sea level to rise quickly and flood former coastlines. The cycles of ice growth and loss are driven by a complex interplay of atmospheric temperature, ocean currents, and orbital variations, creating repeated phases of glaciation and deglaciation. Large ice sheets also affect climate feedbacks. When they expand, they reflect sunlight and cool the planet. When they retreat, they expose darker surfaces, accelerating warming. These feedbacks highlight the fragile balance of Earth's climate system and the sensitivity of sea level to changes in ice volume. Studying past glacial cycles gives scientists insight into possible future shifts as the climate continues to fluctuate. Given this background, a natural question follows. Which plants managed to survive and even thrive under the harsh, cold conditions of the ice ages, and how did they adapt to such extreme environments? In the icy world, tundra and steppe communities were dominated by hardy, low-lying plants that minimized exposure to the cutting wind and frost. Mosses, lichens, dwarf shrubs, and grasses each possessed unique adaptations to the harsh conditions. Lichens, a symbiotic partnership of fungi and algae, were especially resilient. They endured long dry spells and extreme cold, clinging to bare rock where other plants could not take root. Their ability to photosynthesize at low temperatures made them pioneering colonizers of barren landscapes. Dwarf shrubs such as Arctic willow and dwarf birch adopted compact, sprawling forms that reduced wind resistance and retained heat. Their leaves were small, thick, and wax-coated, limiting water loss, a vital trait beneath frozen surfaces. Grasses and sedges with extensive root systems could quickly sprout when brief warm periods appeared during glacial cycles, spreading their seeds over great distances to colonize new ground. Many of these plants entered dormancy during the coldest phases and resumed growth as temperatures rose, a physiological flexibility essential for surviving abrupt seasonal shifts. Their survival created microhabitats for insects, small mammals, and eventually larger fauna, allowing life to persist even in a frozen desert. Following the plant story, the question turns to the animals that endured the same frigid conditions. In the Ice Age, several species rose to dominance thanks to extraordinary adaptations for cold, scarce food, and ever-changing terrain. Mammoths, perhaps the most iconic inhabitants, were covered in dense, layered hair that insulated them against the chill. Their long, curved tusks served multiple purposes, from digging through snow to defending against predators. Their massive size, consistent with Bergmann's rule, reduced heat loss by lowering the surface to volume ratio, and they could clear snow to reach the sparse vegetation beneath, helping them survive seasonal food shortages. Saber-toothed cats, equipped with enormous, elongated canines, stood as top predators. Muscular bodies and short, powerful limbs enabled rapid lunges needed for ambushes on open tundra. Strong jaws, broad skulls, and sharp teeth allowed them to deliver lethal bites, making them effective hunters despite the severe environment. Evidence suggests they may also have possessed thick fur or other insulation to cope with the cold. Giant ground sloths, including megatherids, were built for a slow, deliberate life on open plains and forest edges. Their massive bodies were covered in coarse fur, and their long, curved claws let them pull leaves from tall trees and shrubs. A low metabolism and great size helped retain heat, allowing them to endure cold climates and feed on available foliage even during harsh winters. Mammoths, saber-toothed cats, and these giant sloths all shared special adaptations for the Ice Age chill. Thick layers of subcutaneous fat and dense coats insulated them against biting winds and low temperatures. Mammoths, for example, combined a heavy, woolly coat with a sizable fat reserve that served both as warmth and as energy for long, severe winters. Behavioral strategies were equally vital. Many species migrated seasonally, following herds to richer feeding grounds and avoiding the toughest weather. Social organization protected groups from predators and enabled collective care of young and injured. Saber-toothed cats likely relied on ambush tactics amid thick vegetation, while giant sloths used their powerful limbs to reach resilient shrubs and leaf buds that remained accessible beneath snow. Dietary flexibility also boosted resilience. Numerous megafauna could consume a range of plants, branches, shrubs, roots, available when grass was scarce. Their digestive systems extracted maximum nutrition from such low-quality fare, sustaining them through the toughest periods. Anatomical specializations met environmental challenges directly. Mammoth tusks cleared snow and ice to uncover hidden vegetation, and sturdy limbs with broad feet prevented them from sinking into deep snow, easing movement across frozen terrain.
These extraordinary adaptations, body structure, behavior, and ecological tactics, enabled Ice Age giants to survive in the planet's coldest regions. Their durability illustrates life's remarkable flexibility under extreme climate stress and guides modern scientists as they interpret fossilized bones, preserved remains, and other geological clues that reveal the once thriving ecosystems of the Pleistocene. Large mammals such as mammoths, mastodons, and giant ground sloths left abundant skeletal remains, often uncovered in permafrost or buried in sedimentary layers. These fossils not only prove the animal's existence, but also reveal their size, diet, and aspects of behavior. In exceptionally well-preserved specimens, scientists have recovered soft tissue, hair, skin, and even stomach contents, allowing the study of ancient DNA, reconstruction of genetic lineages, and exploration of evolutionary links between extinct and living species. Mammoth DNA, for example, has illuminated their migration routes and how they adapted to a changing climate. Preserved pollen and plant fragments within icy cores and sedimentary deposits show which flora sustained these ecosystems and how plant communities shifted alongside advancing and retreating ice sheets. Cave paintings and carvings further expand our knowledge by depicting Ice Age fauna. Together with the physical remains, this artistic evidence helps rebuild the complex web of predator-prey relationships and habitat preferences. Isotopic analysis of fossil bones adds detail about diet and migration, indicating how the animals responded to environmental changes.
Collectively, these clues portray dynamic ecosystems in which animals, plants, and climate interacted closely. They demonstrate the richness of Ice Age life and the profound impact of climatic shifts on ancient communities. The deeper we delve into the frozen past, the clearer the evidence becomes of the resilience and eventual collapse of these systems, leading us to the question of why so many remarkable species vanished. The disappearance of many Ice Age animals remains a hotly debated topic, spawning several theories. As glaciers advanced and retreated, conditions across vast regions altered abruptly, destabilizing delicate ecological balances. Species that once thrived in cold tundra or open steppes suddenly lost their habitats and faced a race to adapt or die. The prevailing explanation ties the extinctions to climate change and human activity. Toward the end of the Ice Age, warming trends turned cold zones into milder landscapes, shrinking the ranges of cold-adapted megafauna such as mammoths, mastodons, and giant ground sloths, and depleting their food sources. Grassland and steppe ecosystems contracted, forcing animals into ever smaller refuges. Without rapid aspect or migration, many populations dwindled and vanished. Evidence suggests the climate shifted faster than the animals could evolve or move, prompting mass die-offs. The arrival of humans added another pressure. Equipped with increasingly effective tools, early peoples expanded into new territories, and overhunting likely hastened the decline of already stressed species. The rapid spread of humans across glacial habitats coincided with many extinctions, fueling ongoing debate over the relative roles of human impact and natural environmental change. Some researchers also factor in disease and ecological competition. New predators or rivals that arrived with migrating humans or other species could further destabilize already fragile populations. Genetic analyses reveal that tiny, isolated groups suffered from inbreeding and were less able to withstand natural stress. Overall, the Ice Age extinctions appear to stem from a tangled mix of shifting climate, human impact, and ecological dynamics, a web that underscores how quickly changing environments can imperil species, a lesson as relevant today as it was then. When the ice sheets advanced and retreated, the relentless climate pressure forced plants and animals to devise new ways to survive. Migration became the primary strategy. Organisms trekked across vast ice caps, tundra, or sea corridors in search of more hospitable ground. Large herbivores such as mammoths and northern deer chased the retreating edge of the ice, gravitating toward refugia, small, relatively stable pockets where vegetation persisted. These refugia acted as crucial islands, allowing species to endure severe cold and habitat loss. At the same time, many life forms evolved striking adaptations to the frozen world. Certain plants began producing antifreeze proteins that halted ice crystal formation inside their cells, while others adopted low, bushy, or moss-like growth forms that reduced exposure to wind and chilling. Numerous perennials entered deep dormancy during the harshest months, conserving energy until conditions improved. Among mammals, thick fur, enlarged fat reserves, and behaviors such as hibernation or winter torpor became widespread. The woolly mammoth, clad in a dense coat and bearing a fatty hump, epitomized these evolutionary fixes. Some species also shifted their breeding cycles to align with brief periods of favorable weather, increasing offspring survival. Seasonal migrations timed to the appearance of food resources allowed many animals to follow moving ecosystems. The combination of movement and adaptation not only helped individuals persist, but also reshaped community structures, predator-prey interactions, and continental species distributions. These strategies demonstrate the remarkable resilience of life amid constant environmental flux. As the climate continued to oscillate, plants and animals refined their responses, weaving ever more intricate ecological connections. Understanding these dynamics, especially how predator-prey relationships were reorganized under the relentless pressure of expanding glaciers, offers insight into both ancient and modern biodiversity crises. Across the frozen plains of the Ice Age, massive herbivores such as mammoths and reindeer roamed in great herds, continually devising ways to evade increasingly specialized hunters. In response, saber-toothed cats and giant wolves evolved fierce adaptations, elongated fangs, powerful limbs, and heightened senses that made them formidable predators. Scarce resources amplified the struggle. Predators often relied on long pursuits across vast territories, while prey countered with keen vigilance, herd cohesion, and rapid flight. This back and forth spurred an endless arms race, prompting prey to become faster, more alert, and more social, and hunters to refine tactics, develop ambush strategies, and improve physical tools such as bite force and sensory acuity. Over time, these pressures yielded tightly specialized species perfectly suited to the harsh, open ice. The dynamic between predator and prey rippled through the wider ecosystem, shaping evolutionary pathways. Tough mosses, lichens, and resilient grasses thrived in the tundra, providing stable food sources that sustained the herbivores and, in turn, the carnivores that depended on them. The sheer size and mobility of the large herbivores altered vegetation patterns, keeping expanses open and preventing forest encroachment.
Their movements across endless icy expanses turned them into keystone organisms, dictating the structure of entire communities. When climate shifts and human activity eventually removed many of these giants, the resulting ecological upheavals highlighted the fragile balance of the glacial world. Together, the intertwined adaptations of flora and fauna drove a rapid pace of evolutionary innovation during the Ice Age. This relentless interplay not only forged the remarkable biodiversity of that era, but also laid the groundwork for the complex ecosystems that followed the retreat of the ice. Thick fur and layered fat became the primary response of many mammals to the harsh ice, while some plants evolved mechanisms to survive extreme cold and scarce light. These adaptations not only allowed life to persist through glacial cycles, but also set the stage for later evolutionary paths. As the Ice Age progressed, shifting climates and the pressures they generated spurred waves of species migration. Changing landscapes formed corridors and obstacles that guided both the emergence of new species and the extinction of others, weaving the complex biological mosaic we see today. Understanding this interplay helps us grasp how life constantly remodels itself in rhythm with Earth's natural forces. The cold terrains of the Ice Age reshaped not just the planet's surface, but also human migration. With each advance and retreat of ice sheets, ancient peoples had to quickly adjust to new environments. Climate swings produced a patchwork of habitable zones, often separated by massive ice sheets and tundra, prompting the movement of human groups. The freezing conditions demanded new survival strategies. Early humans fashioned tools for hunting the megafauna of the era: mammoths, woolly rhinoceroses, and northern deer. The scarcity of resources accelerated technological advances, leading to specialized weapons, clothing, and processed hides. These innovations increased survival odds and altered animal populations. Glacial periods were times of rapid climate change that fostered complex social behaviors and cultural practices. Migration routes depended directly on climatic fluctuations. When ice sheets expanded, people retreated to refugia, areas with milder climates such as southern Europe, the Near East, and parts of Asia. As temperatures warmed, these groups spread outward, sometimes crossing newly formed land bridges created by lower sea levels.
Such movements dispersed Homo sapiens and other fauna across continents, encouraging genetic exchange and cultural diffusion. The cold climate also imposed evolutionary pressures on human physiology. Populations in northern regions often developed larger fat reserves and more robust limbs, traits that improved heat retention. Over millennia, these characteristics became entrenched, illustrating how climate shapes both migration patterns and biological makeup. Thus, the ever-changing glacial landscape simultaneously hindered and propelled human development. It forced our ancestors to invent, relocate, and adapt, laying the groundwork for the diversity and resilience of modern humanity. Archaeological evidence from early settlements reveals a story of ingenuity. People established semi-permanent camps near abundant resources, rivers, lakes, or animal migration routes, demonstrating how they mastered a world reshaped by relentless cold and shifting terrain. Stone tools, hearths, and animal bones are the solid signs that people once lived in the icy wilderness. One of the strongest pieces of evidence is the remains of shelters hidden beneath layers of ice and sediment. In Paleolithic caves across Europe, especially in France and Spain, wall paintings show hunting scenes and everyday activities. These pictures tell us that early humans not only survived, but also thought symbolically and built strong social bonds. Some of the art is tens of thousands of years old, proving that even in harsh conditions, they possessed a rich culture. The variety of tools found, scrapers, blades, and points made from stone, bone, and ivory, reveals specialized hunting techniques for massive Ice Age animals, such as mammoths, reindeer, and bison. Each tool reflects deep knowledge of the environment and clever use of available resources. Cut marks on animal bones confirm that they processed carcasses and give insight into how they obtained food. In several regions, fragments of clothing and housing show the ingenuity of these peoples. Preserved skins and bone frames suggest they fashioned warm garments and portable shelters to shield themselves from the cold. Such inventions not only helped them survive, but also reinforced community ties and the transmission of skills across generations. All the archaeological finds, sites, art, tools, and remains paint a picture of resilient groups that actively shaped their surroundings despite relentless glacial challenges. They highlight an extraordinary capacity to adapt, laying the groundwork for the next stage of human evolution: physical and cultural strategies for surviving extreme conditions. Beyond cultural inventions, our ancestors developed anatomical traits that suited the frozen world. Broader bodies and shorter limbs, as described by Bergman and Allen, reduced surface area relative to volume, keeping heat in. A stockier build and the layer of subcutaneous fat added natural insulation, while some groups grew larger nasal cavities that likely warmed incoming air. Culturally, people invented clothing from skins and furs, which trapped heat and blocked icy winds. This need for garments probably shaped social organization, encouraging group hunting and shared skin processing. They also built semi-permanent dwellings from bone, skin, and earth, designed to retain warmth and withstand harsh weather. Fire became a cornerstone of life, providing warmth, cooking food, and making nutrients easier to digest. Equally vital was communal cooperation, sharing resources, hunting together, and keeping fires alive, which boosted the chances of survival for both individuals and the whole group. Cultural adaptations handed down survival know-how from one generation to the next, forging a shared toughness against the relentless cold. Biology, clothing, shelters, fire, and cooperation blended into a single survival strategy, illustrating how people not only endured the icy grip of the Ice Age, but also managed to thrive. The ingenuity of our ancestors went far beyond mere subsistence. It laid the foundation of human resilience that still echoes today. As the climate grew harsher, Ice Age peoples invented tools and technologies that expanded their capabilities. They fashioned fur garments that trapped heat, using sharp stone blades and scrapers to turn raw hides into wearable layers. Over many generations, the cutting edges became finer, allowing the stitching of multi-layered clothing that minimized heat loss. The frigid environment also spurred advances in shelter building. Early dwellings combined animal bones, wood, and skins to create temporary refuges that kept out the cold. Natural materials were employed to line these structures and fire pits, which not only warmed the interiors but also became social hubs. Fire itself became a crucial instrument, providing warmth and enabling the cooking of food that increased nutritional value and energy intake.
Mastery of fire-making, such as striking sparks from stone, marked a major technological milestone. Beyond clothing and fire, Ice Age groups produced composite tools by joining stone with bone or horn. These multi-component implements boosted hunting efficiency and meat processing, vital when resources were scarce. Spears and atlatls, for example, exposed the range and force of throws, allowing hunters to pursue large game from safer distances. Such durable, versatile tools demonstrated a deep understanding of material properties and flexible thinking required for survival in an unpredictable, cold climate. Collectively, these innovations reveal a profound capacity to adapt to the pressures of the Ice Age. They reflect not only technical skill with raw materials, but also an evolving grasp of how to reshape the environment to meet basic needs. The development of sophisticated tools and cooperative practices paved the way for later cultural and evolutionary progress, embodying the resilience and creativity that defined human life during one of Earth's harshest climatic periods. In the open, frozen tundra, early hunters relied on simple methods suited to large prey. As they gained experience, they refined their tactics, coordinating ambushes and employing spears and atlatls, which made hunting mammoths, bison, and reindeer far more efficient. The meat and hides of these animals became essential food and material for shelter and clothing. Gathering grew equally sophisticated. People learned to follow the seasonal ripening of fruits, nuts, and tubers across different regions, observing microclimates and ecological zones so they could move strategically and collect the most food during lean periods. This seasonal mobility required flexible social organization and constant communication, which in turn strengthened cooperation within the work. New tools, such as scrapers and grinding stones, let them extract more nutrients from plants, while diverse resources spurred the development of storage techniques, drying, fermenting, and other preservation methods that kept supplies viable through harsh winters. These practices not only ensured survival, but also reinforced group cohesion and the transmission of knowledge, key foundations of early human culture. The need to exploit a wide range of resources accelerated technological progress, leading to increasingly specialized implements for specific tasks. As hunting and gathering became more demanding in the unpredictable glacial environment, pressure from the frozen world drove innovation, laying the groundwork for more complex behavior. Improved survival strategies eventually gave rise to symbolic and artistic expression. The stark, majestic landscapes of the Ice Age served as a backdrop for the emergence of early art. In the dim chambers of caves, people used natural pigments of ochre and charcoal to paint bison, horses, reindeer, and other animals. These images likely held ritual or magical meaning, tied to hunting success or spiritual belief, and their repeated motifs across distant sites suggest a shared cultural significance and a budding sense of community rooted in the environment. Beyond cave paintings, ornaments made from shells and animal teeth indicate an awareness of symbols and status. Such items could signal social bonds, personal identity, or participation in communal ceremonies. In a climate where durable materials were scarce, any object that could endure became a potent symbol. Symbolic behavior also extended to body modifications and ritual actions, further illustrating the deep connection between the challenges of the natural world and the birth of human culture. Burial sites with grave goods reveal that ancient peoples believed death was not final, and that some form of existence continued beyond the physical world. This spiritual dimension, expressed through symbolic actions, shows that art was more than a means of communication. It was a way to comprehend their environment and their place within it. The glacial climate shaped not only survival strategies, but also the very mindset in which symbols, stories, and spiritual ideas became integral to daily life. Faced with an unpredictable climate, people turned to creativity to influence their world and to find meaning amid constant change. Alternating cold and warm periods dictated the dynamics of human populations, steering migration, adaptation, and survival. When temperatures fell, habitable land shrank, forcing groups into refugia, areas where conditions remained tolerable. These refuges often turned into population hubs, encouraging genetic exchange and spawning cultural innovations needed for harsher conditions. Conversely, warm interstadials opened new territories, exposing fresh landscapes, new food sources, migrating animals, and diverse plants. The relative warmth spurred population growth and prompted migrations across Eurasia and beyond. However, expansions were rarely smooth. Sudden climatic shifts could wipe out habitats, compelling people to retreat or adapt rapidly. The ongoing cycle of contraction and expansion produced a shifting demographic picture marked by periodic declines and settlement bursts, which, in turn, affected genetic diversity and evolutionary pathways. Climate variability also drove technological and social development. Resource shortages led to new hunting and gathering tools, while harsh conditions fostered complex communal structures for collective survival. During cold spells, ancestors refined clothing, shelters, and hunting techniques, not only preserving life, but also laying the groundwork for cultural and technical achievements passed down through generations. Overall, the influence of climate on ancient human groups highlights remarkable resilience and adaptability, underscoring the environment's central role in evolutionary history. Archaeological discoveries, such as Cro-Magnon and Neanderthal remains, have reshaped our understanding of how people adapted to extreme cold, shifting landscapes, and scarce resources, providing tangible links to an evolutionary past and revealing the physical adaptations that enabled survival in the Ice Age. A sturdy, broad-bodied build and enlarged nasal passages helped early humans warm the frigid air before it reached their lungs. Those features show how the human body adjusted to the Ice Age's chill. The remains of Cro-Magnon people, the first anatomically modern humans, mark a leap toward more sophisticated tools, artistic expression, and organized societies. Well-preserved fossils reveal a range of behaviors, from crafting delicate implements and ornaments to conducting symbolic rituals. These inventions not only boosted survival odds in a harsh, glacial world, but also sparked the cultural evolution that eventually produced today's humans. Comparing Cro-Magnons with Neanderthals, highlights a complex interaction that left deep genetic traces. The discoveries go far beyond bone analysis. They paint a vivid picture of human resilience and ingenuity amid severe climate. Associated hearths, cave paintings, and tools demonstrate how these ancestors exploited their surroundings, hunted megafauna, and forged the social bonds needed to endure the cold. The evidence underscores that both biological and cultural flexibility were crucial during continual environmental shifts. Placing these ancient remains within the broader Ice Age context shows that our forebears were not passive victims of nature, but active shapers of their fate. The deeper we probe their lives in a frozen world, the clearer it becomes that human history is tightly woven with Earth's climatic upheavals. This foundation leads to the next chapter: how glaciers and ice sheets reshaped the planet's surface, altering landscapes and influencing human development. Massive ice sheets advanced and retreated like slow, relentless sculptors, carving bedrock and reforming valleys and plains. Gravity pushed thick ice outward from polar and high-altitude accumulations, and the continuous flow exerted immense pressure on the ground beneath. This pressure drove both erosion and deposition, permanently marking the terrain. Erosion was the chief transformative force. As glaciers moved forward, they scraped away surface material, while tiny ice crystals ground rock like natural sandpaper, widening and deepening existing valleys and turning river gorges into broad troughs. The weight of the ice stripped away soil and loose rock, exposing hard bedrock and creating stark, often majestic relief. At the same time, glaciers left behind huge deposits of unsorted debris, glacial till, that formed moraines marking the furthest reach of the ice. When the ice melted, meltwater filled the carved basins, creating lakes and wetlands, or pooled behind moraines. The sheer scale of glacial activity also produced distinctive landforms, such as drumlins, streamlined hills molded by the moving ice, preserving the story of these ancient ice sheets for us to read today. Long, winding ridges and the deposits left by meltwater streams in subglacial channels silently record the dynamic processes that once shaped the ice. These forms not only reveal ancient ice movement, but also continue to influence drainage patterns and ecosystems today. Glaciers and ice sheets permanently altered the Earth's surface, carving a majestic, complex landscape that bears the history of relentless ice change. Glacial activity produced some of the most striking and recognizable relief, preserving the story of ice flow. Among the most prominent features are U-shaped valleys and fjords, classic signs of ancient glacial erosion that showcase both the power and advance of ice. U-shaped valleys, or glacial troughs, develop when a moving glacier deepens and widens a pre-existing river valley. Unlike river-cut valleys, the glacier scrapes the floor and sides, creating a broad, flat bottom with steep walls. These valleys often appear where tributary glaciers once joined the main glacier, preserving evidence of large-scale erosion over thousands of years. Fjords are essentially drowned U-shaped valleys. After the ice retreated, rising sea level filled the deep, narrow valleys with seawater, forming narrow inlets flanked by towering cliffs. They occur where glaciers carved deep valleys below today's sea level, such as in Norway, New Zealand, and parts of Canada. Their creation required both powerful glacial erosion and subsequent sea level rise, and their depth and scenery have made fjords iconic coastal landscapes, embodying the immense forces of the Ice Age. Smaller landforms, moraines, drumlins, and roches-moutonnées, also record the history of ancient ice sheets and their impact on the terrain. As glaciers advanced and withdrew, they left numerous characteristic features that silently testify to their former paths. Moraines are piles of rock, soil, and unsorted debris deposited directly by the ice. Lateral moraines line the sides of a glacier, while terminal moraines mark the furthest advance, indicating both the direction of flow and periods of stability. Drumlins are elongated, streamlined hills of glacial material reshaped by moving ice, pointing in the direction of ice movement. Their smooth, drop-shaped outlines reveal the direction and strength of the ice flow that formed them. Drumlins often appear in clusters, marking a dynamic stage when a glacier reshaped the underlying drift, leaving a landscape that records ancient meltwater pathways. Their alignment and spacing allow geologists to infer the direction and speed of ice movement during the last glacial maximum. Osies are winding ridges created by meltwater streams flowing beneath the ice. As the glacier melted, sediment-laden water deposited sand and gravel in tunnels under the ice. When the ice retreated, these sediment-filled tunnels remained as sinuous ridges. Osies trace subglacial water routes and reveal the timing and direction of meltwater flow that cut through the glacier or its bed. Each of these forms, arenas, drumlins, and osies, preserves a record of ice advance, accumulation, and retreat. By studying them, geologists reconstruct the paths of ancient ice sheets, their pauses, and their departures, witnessing the immense power that sculpted the planet's early landscapes. Glacial erosion dramatically reshaped Earth's surface, altering the locations and characters of lakes and rivers. Advancing and retreating ice, through its weight and motion, carved deep valleys, fjords, and basins, often converting former landforms into new water bodies. These basins later filled with meltwater, becoming the numerous lakes that persist today. Uneven glacial erosion also dictated river courses. Advancing ice could block existing valleys, form natural dams, divert streams, or create temporary upstream lakes. When the ice melted, the dams sometimes failed, unleashing massive floods that cut new channels and redistributed sediments. The resulting landforms, streamlined hills and sand-filled plains, guided later river flows. Sediment carried by meltwater further complicated drainage networks. Accumulations of gravel, sand, and silt determined where rivers could meander or fix their beds. In some regions, glacial activity produced broad, gently sloping terrains dotted with small lakes, a bowl lake landscape formed as buried ice blocks slowly melted. These irregularities created a mosaic of water bodies and river courses, influencing local ecosystems and human settlement patterns. In some, the relentless force of glaciers carved the modern pattern of lakes and rivers. Ice movement not only reshaped land outlines, but also re-engineered drainage systems, forming complex water pathways and water-filled basins that continue to define the Earth's surface long after the ice vanished. Understanding these processes shows how ancient ice sheets forged the hydrological features of our planet. To reconstruct past glacial landscapes, scientists meticulously analyze geological and sedimentary evidence, focusing on the forms left by ice, moraine ridges, drumlins, and osies to piece together the ancient environment of Earth. Glaciers leave a tangible record of their past movements, letting scientists gauge their former size and dynamics. By mapping these landforms across different regions, researchers reconstruct the outlines of ice sheets and trace their retreat over millennia. Sedimentary deposits are equally crucial. Unsorted morainic layers deposited directly by ice capture brief moments of advance and withdrawal, while seasonal lake sediments, varved clays, provide yearly snapshots of temperature and precipitation during glacial periods. Chemical signatures within these layers reveal ancient environmental conditions. The ratio of oxygen isotopes in marine and terrestrial deposits helps estimate past temperatures and ice volumes, turning sediment composition into climate data for ice sheet models. Pollen grains and microscopic organisms trapped in the sediments disclose vegetation patterns and ecological zones of each glacial phase, enriching reconstructions of both landscape and climate. Remote sensing and geochronology have sharpened these methods. Radiocarbon dating and optically stimulated luminescence pinpoint the age of sedimentary layers, establishing a chronological framework for landscape change. Together, the varied evidence produces dynamic reconstructions of glacial terrains, showing how ice sculpted the Earth's surface over tens of thousands of years. These reconstructions clarify why ancient glaciated landscapes continue to shape today's environment. The lasting imprint of ice profoundly influences modern geography, ecosystems, and human land use. Among the most striking long-term legacies are fjords, valleys, and moraines. Massive ice shields carved deep valleys into mountain ranges, creating the dramatic fjords that line coastlines in places such as Norway and New Zealand. These deep, glacially carved bays host unique habitats and affect local weather. Moraines, piles of debris left by retreating ice, form fertile plains and natural groundwater reservoirs, guiding agriculture and settlement patterns in many regions. Glacial erosion and deposition also reshaped drainage networks and sediment distribution, giving rise to extensive alluvial plains and delta systems that dictate contemporary river courses and coastal ecosystems. These deposits determine soil fertility, farming practices, and biodiversity. Perhaps the most enduring impact lies in the Earth's crust itself. The immense weight of ice sheets depressed the underlying land, a process known as isostatic loading. After the ice melted, the crust slowly rebounded, a phenomenon called isostatic uplift, altering local topography and creating new landforms. This uplift continues to modify the landscape long after the glaciers have vanished. The retreat of massive ice sheets lifted former seabeds, reshaping today's coastlines and influencing ocean currents. Glacial valleys and lakes still tweak local microclimates, and meltwater from ancient glaciers remains a vital source of fresh water for ecosystems and human use. As the ice weight vanished, the crust rebounded, slowly raising the land that once held the ice and altering shoreline elevations over centuries. Meltwater flooded low-lying coasts, carving inland seas and the deep fjords that define Scandinavia, New Zealand, and parts of North America. Glacial erosion produced the classic U-shaped valleys and steep walls that, once submerged, became some of the planet's most dramatic shorelines. Along the margins, retreating ice left unsorted till, gravel and silt, moraines, drumlins, and other deposits that waves later reshaped into barrier islands, deltas, and estuaries. These features host rich plant and animal communities, underscoring the lasting ecological imprint of the Ice Age. Together, erosion and sediment buildup forged complex coastlines of fjords, estuaries, and barrier islands that still dominate many famous seascapes. Permafrost, permanently frozen ground, stabilizes polar soils, limiting erosion while generating distinctive forms such as polygons, pingos, and thermokarst through repeated freeze-thaw cycles. Periglacial processes tied to this frozen layer continue to sculpt cold region landscapes long after the glaciers vanished. Cold temperatures cause water in the soil to freeze and expand, heaving up ground and stones and forming distinct patterns of sorted circles and bands. These textures record the ongoing struggle between ice-rich soils and seasonal temperature swings. When permafrost thaws, thermokarst landscapes appear, irregular depressions, sinkholes, and a hummocky surface created by ground subsidence. Such features reshape the terrain and alter hydrology, giving rise to lakes, ponds, and wetlands that become vital habitats. The extent and stability of permafrost are tightly linked to climate. During the cold phases of the last ice age, permafrost spread widely. Fluctuating temperatures intensified periglacial processes, carving complex surface patterns and influencing the movement of sediments and organic matter, thereby affecting local ecosystems and the carbon cycle. As the climate warmed at the end of the last glacial period, permafrost began to melt, releasing stored greenhouse gases and dramatically reshaping the landscape. The retreat of ice triggered a cascade of climatic shifts that transformed Earth's surface and atmosphere. Rising global temperatures, driven by weakened ice albedo feedback, increased greenhouse gas concentrations and restructured oceanic and atmospheric circulation, redistributed heat worldwide. Shrinking ice exposed darker land and water surfaces, which absorbed more solar energy and amplified warming. Additional greenhouse gases, carbon dioxide and methane, released from thawing soils and oceans, further boosted atmospheric heat retention. Occasional volcanic eruptions altered atmospheric composition and temporarily cooled the climate, but their influence was minor compared to greenhouse gases. Changes in ocean currents and atmospheric patterns modified salinity and stratification, reshaping major currents that transport heat across the planet. The new circulation patterns supported a warmer climate, moving heat more efficiently toward the poles and equator than during glacial times. Together, the loss of ice reduced surface albedo, creating a positive feedback loop that accelerated warming. The transforming landscape opened new migration routes and habitats, while also setting the stage for rising sea levels. This sequence of events illustrates the profound transition from the frozen world of the last ice age to the relatively warm and stable climate we experience today. The retreat of the massive ice sheets that once covered much of the northern hemisphere reshaped the planet's surface and set in motion a dynamic interaction between climate, sea level, and coastlines. As the ice melted, the global sea level rose, flooding low-lying regions, forming shallow seas, and creating fertile coastal plains. During glacial maximums, vast continental shelves were exposed, only to be submerged again as the climate warmed. These continual shifts moved shorelines, altered sediment deposition, changed erosion patterns, and reshaped ecosystems. Rising waters forced some habitats underwater while exposing new ones, compelling species to adapt, migrate, or disappear. For early humans, this meant gaining fresh resources or losing familiar hunting grounds. In the oceans, freshwater influx from melting ice temporarily disturbed circulation, influencing climate patterns far beyond the immediate area. The altered circulation changed temperature and salinity gradients, affecting nutrient distribution and the productivity of marine communities. The overall melting of the ice sheets acted as a catalyst for coastal transformation and ecological evolution that still shapes the Earth today. The transition from a glacial to an interglacial period, driven by subtle shifts in Earth's orbit and atmospheric composition, produced new habitats, redistributed water resources, and reshaped river courses, leading to the development of fertile floodplains and wetlands. These new lands first hosted hardy grasses and shrubs, which laid the foundation for richer ecosystems, supporting herbivores, then predators, and boosting terrestrial biodiversity. When the climate finally steadied, forests re-emerged across many regions, providing dense habitats for countless species. This shift marked a pivotal turn toward greater biodiversity. Cold-adapted organisms either migrated northward or retreated into refugia, while others evolved new traits suited to warmer conditions. The changing climate imposed evolutionary pressure that spurred both the rise of new species and the extinction of others, reshaping community composition. These dynamic processes forged a new equilibrium that underpinned the complex ecosystems of today's interglacial world. Understanding the natural and ecological fallout reveals how tightly climate and life are intertwined. The move from ice to warmth not only altered landscapes, but also redefined relationships among species, ecosystems, and the planet itself. This intricate dance set the foundation for the rich biological diversity we see now, and prompts reflection on how current climate shifts might shape Earth's future. As the grip of the last ice age weakened, plants and animals faced a sharply altered climate. Species thriving in harsh cold had to adapt quickly or disappear. Many plants migrated toward more favorable zones. Tundra vegetation, for example, moved northward behind retreating ice sheets, creating new habitats where life had previously been impossible. These shifting plant communities often became the base of emerging ecosystems, supporting herbivores and the predators that followed. Animals responded in varied ways. Mammoths, woolly rhinoceroses, and saber-toothed cats were pushed into isolated refuges as their extensive ranges shrank. Some survived in cold, high-altitude or northern pockets, but many vanished under the rapid environmental change and growing human pressure. Smaller, more adaptable species, deer, bison, and diverse grazers, expanded their ranges, exploiting fresh vegetation and open landscapes. Migratory birds altered their timing and routes to stay in step with plant cycles, ensuring access to food during breeding and migration. The end of the Ice Age also triggered a cascade of marine changes. Fresh meltwater altered ocean salinity and currents, reshaping the distribution of marine life. Fish moved toward new spawning grounds, and marine mammals colonized newly exposed coastal areas. In many places, forests replaced tundra, offering complex habitats for a broader fauna. The emerging environment generated evolutionary pressure that led numerous species to develop novel forms and adaptations. The swift, often harsh transitions caused extinctions, but also highlighted nature's resilience and flexibility. The interplay of climatic shifts and biological responses underscores the profound influence of the environment on life's evolution. By the close of the Ice Age, human activity began to leave a noticeable imprint on changing landscapes and ecosystems. Armed with simple tools and adaptable strategies, early peoples started to affect their surroundings, initially through hunting and gathering, setting in motion impacts that would endure for millennia. Human activity gradually reshaped the post-glacial landscape, setting the stage for agriculture and permanent settlements. One of the most striking early impacts was the extinction of many megafaunal species. As people spread into new areas, hunting helped drive large animals such as mammoths and saber-toothed cats to extinction. This loss upset ecological balance, altered vegetation, and disrupted nutrient cycles, often restructuring plant communities and influencing the development of forests and meadows. The shift to farming marked a decisive turning point. Moving from nomadic gathering to settled agriculture, people cleared fields, built irrigation, and increasingly domesticated plants and animals, dramatically transforming the terrain. These practices accelerated soil erosion, changed local water regimes, and introduced new species that frequently outcompeted native flora and fauna. In later periods, urban growth and forest clearing continued the trend. Expanding towns replaced woods, and natural habitats deteriorated. Land use changes also fed back into the climate system. By altering the surface, humans increased greenhouse gas emissions and could affect climate patterns and the speed of natural changes. Overall, humanity's role evolved from a relatively passive participant to an active ecosystem engineer. These early interactions laid the groundwork for the complex relationships between people and the environment that still shape the planet. And recognizing this influence is essential for understanding past and future climate dynamics. To determine when the last ice ages ended, scientists employ a suite of dating techniques from geochronology and paleoclimatology. Radiocarbon dating, which measures the decay of carbon-14 in organic material, can date samples up to about 50,000 years old and provides precise ages for recent transitions, including the final retreat of the last glacial period. For older events beyond radiocarbon's reach, researchers turn to oxygen isotope ratios, oxygen-16 versus oxygen-18 in ice cores or marine sediments. These ratios serve as reliable proxies for past temperatures and ice volume, allowing accurate timing of ice sheet growth and melt. Ice core layers themselves preserve annual and even seasonal information. Variations in dust, volcanic ash, and trapped gas bubbles act as chronological markers, linking different core sections and aligning them with global events. Finally, orbital, astronomical tuning matches isotope records to calculated changes in Earth's orbital eccentricity, tilt, and precession. By correlating climate cycles with known orbital patterns, scientists refine the timing of deglaciation and reconstruct how ice sheets responded to orbital forcing. These methods give a full picture of how the end of the ice ages unfolded. They show not only when the ice retreated, but also how fast and in what order natural changes happened, letting us tell whether the shifts were slow or sudden. For a long time, scientists have debated whether glacial terminations were abrupt or gradual, building many hypotheses from paleoclimate data. Current work shows that the move to interglacial periods usually mixed quick spikes with slower trends, making the picture more complex than a simple, steady warming. One well-known idea holds that events such as the Booling-Allerud warming about 14,700 years ago unfolded over decades or centuries, so parts of the Ice Age finish could happen rapidly. These bursts are often linked to sudden releases of stored greenhouse gases, especially methane, from permafrost and subglacial lakes, which boost warming and can push the climate past tipping points. Other evidence points to a more gradual path, driven by slow but steady changes in Earth's orbit, ocean circulation, and greenhouse gas concentrations. Over millennia, these factors altered insolation and sea level, steadily shrinking the ice sheets. The combination of slow forces and occasional abrupt events creates a mosaic of transitions. Some intervals are marked by rapid climate jumps, others by long, steady changes. Ice core and sediment records confirm that past terminations were not a single event, but a series of fluctuations, with rapid warming episodes eventually leading to a relatively stable interglacial. This highlights the climate system's multifaceted response, involving both tipping points and gradual shifts. Understanding these patterns helps improve models of how today's and future climates will react to ongoing human influence. Studying ancient deglaciations also reveals how the dynamics of ice sheets regulate climate. When ice melts, sea level rises, Earth's albedo changes, and ocean currents are altered, redistributing heat worldwide. These feedbacks often amplify warming, causing further melt and instability. Recognizing the thresholds and tipping points of past transitions equips scientists to identify similar vulnerabilities in the modern climate system. The paleoclimatic record shows how tightly the ocean and atmosphere are linked, especially through the Atlantic meridional overturning circulation that regulated climate during deglaciation. As ice melted, fresh water poured into the seas, lowering salinity in some regions while raising it elsewhere. These salinity shifts altered water density, reshaped heat distribution, and accelerated warming phases. The evidence underscores that a disturbance in one part of the Earth system can cascade into broad climate change. When researchers examine the end of past ice ages, they build models that incorporate historic feedbacks, thresholds, and response times. Such models help policymakers gauge the risk of rapid modern climate shifts. Lessons from the past thus serve as a vital compass for forecasting and action amid ongoing warming. During major glacial transitions, the global ocean did not stay static. Its salinity, temperature, and circulation underwent profound reorganization. Expanding ice sheets trapped vast amounts of water on land, dropping sea level by up to 120 meters and exposing continental shelves. This exposure broke established current patterns and triggered a chain of effects on water properties worldwide. The removal of fresh water from the ocean increased salinity where evaporation outpaced precipitation, while elsewhere the influx of meltwater made the water less salty. Uneven salinity changed water density, which in turn modified thermohaline circulation, the planet-wide conveyor of heat and nutrients. For example, during deglaciation, the surge of fresh water into the North Atlantic temporarily weakened the overturning circulation, producing regional and global climate shifts. Ocean temperature was closely tied to ice sheet dynamics. Over growing ice sheets, colder surface water formed, reinforcing sea ice and further insulating the ocean from the atmosphere, which reduced heat exchange. Conversely, during warmer interstadial periods, massive releases of fresh meltwater disrupted temperature gradients and circulation routes. These reorganized currents altered nutrient distribution, marine ecosystems, and climate regulation. Modified pathways could either link or separate ocean basins, influencing heat and salt exchange on a planetary scale. Ocean dynamics also played a decisive role in either amplifying or curbing ice sheet growth, creating feedback loops that either promoted or halted glacial advances. Beyond climate, changing ocean chemistry and circulation left lasting imprints in the geological record, preserving evidence of dramatic sea level swings. Flooded landscapes now offer a glimpse into past sea level fluctuations. During cold spells, sea level fell far enough to reveal dry land bridges and extensive coastal plains. routes that ancient peoples and migrating species once used. Physical traces of change are visible in the underwater landscape, recorded by marine geology and high-resolution sonar maps. Submerged terraces mark former coastlines, while drowned river valleys preserve the courses of freshwater streams that existed before the sea rose. On the floor of the North Sea, for example, vast flooded areas once served as land corridors, showing how lower water levels opened migration routes across Europe and Asia. Similar submerged terraces along the Atlantic coasts of North America and Europe reveal previous shoreline positions and confirm the scale of sea level swings. Coral reefs and sunken coastal forms are also key indicators. When sea level was low, many reefs grew on exposed land. Their fossilized remains now lie beneath the water, fixing the sea's position at various times. Sediment cores from drowned regions record changes in depth and climate, providing a chronological account of sea level fluctuations. Combined with radiocarbon dating of organic material from underwater deposits, these data allow researchers to reconstruct the timing of sea level rises and falls with great precision. These submerged landscapes are crucial not only for understanding ancient sea level dynamics, but also for illustrating how glacial age climate shifts reshaped the Earth's surface. Advancing and retreating ice sheets repeatedly altered coastlines, leaving a legacy beneath the waves. The evidence deepens our grasp of how climate oscillations sculpted the planet's geography and created pathways for human migration and ecological transformation. Land bridges, such as Beringia, profoundly influenced species distribution during the ice ages. As massive ice sheets advanced and retreated, sea level could drop up to 120 meters below today's level, exposing extensive continental shelf plains. Recently uncovered corridors, hidden underwater during interglacial periods, dramatically reshaped the Northern Hemisphere's geography. The Bering Land Bridge, linking Asia and North America, exemplifies how these connections became vital routes for both animals and people. During low sea level phases, mammals such as mammoths, bison, and camels crossed the bridge, exploiting expanding tundra resources. Following the game, human groups also used the passage, marking one of the earliest known steps in populating the Americas. These migrations were more than simple relocations. They generated complex ecological exchanges, genetic mixing, and the spread of flora and fauna between continents. The availability of land bridges triggered significant evolutionary events. In interglacial periods, isolated populations diverged and evolved independently, fostering regional diversity. During glacial maxima, cold-adapted species rapidly colonized new territories, while fragmented habitats sometimes gave rise to specialized subspecies or entirely new species. When the ice sheets melted and sea level rose again, the bridges disappeared beneath the water, isolating populations in new, often secluded habitats and steering further evolutionary change. The rise and fall of sea level thus not only directed migrations, but also reshaped ecological dynamics and biotic connections across the globe. The creation of land bridges was a key driver of biological and cultural change during the Ice Age world, shaping migration routes. Ocean currents added another layer of influence, reshaping climate as they moved heat across the planet. When ice sheets grew or shrank, they altered the shape of continents and ocean basins, which in turn redirected major currents such as the Gulf Stream and the Antarctic Circumpolar Current. During glaciations, massive ice in the northern hemisphere blocked the usual flow of warm equatorial water toward higher latitudes.
The Gulf Stream often weakened or shifted, sending less warmth to northern Europe and North America and helping maintain colder, more stable conditions. In some regions, redirected currents amplified cold surface waters, fostering sea ice growth and further regional cooling. These heat redistribution changes also impacted the thermohaline circulation, the global conveyor belt driven by differences in water density. In cold periods, expanding sea ice and large inputs of fresh meltwater slowed this circulation, creating a bottleneck that reduced heat transport and reinforced cooling, a positive feedback loop. When the climate warmed and ice retreated, the freshwater input dwindled, the conveyor belt regained strength, spread heat more evenly, and softened the global chill. Shifts in currents affected not only temperature but also storm tracks, monsoons, and precipitation patterns, triggering broad ecological and atmospheric changes that influenced ice sheet stability and the overall climate system. Research shows that these massive, moving water flows occupied a central role in Earth's climate history. A crucial question is how the influx of fresh water, especially from icebergs, altered ocean circulation and climate stability. Huge icebergs breaking off expanding ice sheets drifted into ocean basins and released vast amounts of fresh water. Sudden pulses of this water lowered salinity and density in key passages like the North Atlantic, hampering the sinking of cold, dense water that powers deep currents. This disruption could weaken the Atlantic meridional overturning circulation, leading to sharp regional cooling by curtailing heat flow from the equator.
Such freshwater events often coincided with abrupt climate shifts, rapid warmings followed by sudden cooling, illustrating the delicate balance between ice, water, and climate. Fresh water from melting ice altered both the area and stability of sea ice. When meltwater influx increased, sea ice could spread further, insulating the ocean from atmospheric heat and reinforcing cooling trends. Conversely, periods of weak influx often lined up with warmer interstadials, allowing strong currents to revive and redistribute warmth around the globe. The impact of meltwater was not confined to isolated regions. It played a role in the cyclic climate variability of the entire glacial epoch. The frequency of iceberg carving and the volume of runoff depended closely on the growth and breakup of massive ice sheets, creating feedback loops that regulated both local environments and the global climate. To grasp this dynamic, scientists examine how individual pulses of fresh water disturbed the delicate balance between ocean and atmosphere, and they read the ancient climate record preserved in sediments and varves. Modern approaches use sediment cores and varve analysis as deep time archives, capturing detailed information that allows precise reconstructions of past climate swings and oceanic behavior. A core is like a time capsule, layered with sediments that accumulated over thousands of years. As particles settled from the water column, they carried clues about their era, mineral composition, organic material, and microfossils. By studying the makeup and order of these layers, researchers infer changes in ocean productivity, circulation routes, and the extent of ice cover. Shifts in microfossil types and abundance reveal fluctuations in nutrient availability and water temperature, adding nuance to sedimentary interpretations. Isotopic analysis further probes chemical signatures within the sediments. Ratios of oxygen-18 to oxygen-16 in carbonate shells of marine microorganisms are especially telling. During cold spells, more oxygen-16 becomes trapped in ice, leaving the ocean enriched in oxygen-18. Consequently, shell chemistry records variations in global ice volume and temperature. Carbon isotopes and other elemental markers also convey information about ocean productivity and the carbon cycle, both tightly linked to climate shifts. Merging sediment stratigraphy with isotopic data yields a detailed timeline of ocean temperatures, sea level changes, and circulation patterns throughout the glacial periods. These reconstructions not only deepen our understanding of ancient climate systems, but also provide valuable analogues for today's ocean atmosphere changes, illustrating how Earth might respond to ongoing climatic variability. As research progresses, the integration of multiple methods sharpens our picture of the complex interactions that have shaped the planet's climate history. The profound reorganization of the ocean during glaciations, when sea level often fell more than 100 meters, reshaping coastlines and altering nutrient and heat distribution, disrupted established circulation, especially the thermohaline conveyor that moves warm and cold water masses and regulates global climate. Sedimentary cores reveal a tight connection between the strengthening or weakening of ocean currents and climate swings, showing how sensitive these systems are to the size of ice sheets and the influx of fresh water during periods of ice buildup or melt. When large ice sheets expanded or contracted, they reshaped salinity and temperature gradients in the North Atlantic and the Southern Ocean, altering the power and stability of major oceanic pathways. These shifts in circulation sparked rapid climate changes, with some regions suddenly cooling while others warmed, depending on how heat was redistributed. Investigating ancient ocean responses uncovers feedback loops among ice sheets, currents, and the atmosphere, underscoring the Earth's climate as an interconnected whole. During deglaciations, melting ice dumped massive pulses of fresh water into the seas, frequently disrupting currents and launching planetary-scale climate shifts. Such episodes serve as analogues for a possible future in which accelerated melting could again upset modern circulation and trigger abrupt climatic events. The relevance of these processes extends far beyond historical curiosity. They highlight the necessity of a stable ocean for maintaining climate balance. Insights from past oceanic changes help interpret today's trends, including the recent weakening of the Atlantic meridional overturning circulation, a driver that can affect regional and global climates. Continuing to decode ancient ocean dynamics provides essential reference points for forecasting and mitigating future climate variability, emphasizing the ocean's central role in Earth's climatic resilience. During the tumultuous climate oscillations of the glacial era, marine life faced severe challenges and remarkable opportunities for adaptation. The growth and retreat of ice sheets dramatically altered sea level, coastlines, and underwater landscapes, forcing organisms to adopt diverse survival strategies. Many species migrated long distances to remain within suitable temperature zones, moving from low-latitude tropics toward colder northern or southern waters as ice expanded. When ice receded, other species broadened their ranges, colonizing newly exposed continental shelves and shallow seas created by falling sea levels. Physiological adjustments were crucial. Cold-adapted species developed thicker insulation, marine mammals accumulated more blubber, and mollusks reinforced their shells to withstand frigid conditions. Some plankton communities, the foundation of marine food webs, adjusted to shifting nutrient supplies linked to changing currents and ice cover. Seasonal polynyas, open water patches amidst sea ice, became vital feeding and breeding grounds, sustaining diverse communities even in icy surroundings. Ice sheet dynamics dictated not only where organisms could live, but also how they interacted within ecosystems. After ice retreat, fresh habitats were quickly occupied by benthic and pelagic species, and isolated populations often evolved into new species. Conversely, extensive ice limited open water, curbing movement and genetic exchange, leading to population declines and local extinctions.
The resilience of marine life amid these fluctuating conditions underscores the close tie between cryospheric changes and biological adaptation, reinforcing the ocean's pivotal role in Earth's climate system. Migrations, physiological shifts, and ecological changes have left clear marks in the fossil record, giving us valuable clues about ancient environments. How marine life responded to past glacial swings not only tells the story of life's history, but also helps predict how today's climate will affect ocean ecosystems. Reconstructing Earth's icy past relies on a suite of dating techniques that pinpoint the age of sediments and fossil remnants from glacial periods.
Scientists examine the physical, chemical, and mineral properties of samples, each revealing the timing of glacial events and the life that existed then. Radiometric dating is a cornerstone method. Uranium series dating, for example, is applied to calcium carbonate formations such as cave stalagmites, yielding ages up to several 100,000 years. Potassium-argon and argon-argon techniques determine the age of volcanic ash layers embedded within sediments. These tephra layers serve as precise time markers, constraining the age of surrounding deposits and fossils, and complement biostratigraphy and paleomagnetic dating. Biostratigraphy matches assemblages of fossils, pollen, microfauna, and animal remains across different sites, establishing relative ages and tracking migration routes. Paleomagnetism studies the ancient orientation of Earth's magnetic field recorded in rocks and sediments. Because magnetic reversals occurred globally at known times, their signatures provide a reliable chronological framework. Luminescence dating, both optically stimulated and thermoluminescence, measures the buildup of trapped electrons in mineral grains after exposure to light or heat. The known rate of energy accumulation lets researchers calculate the time elapsed since the last illumination or heating event. Combined, these methods create a detailed temporal map of glacial deposits and the organisms they contain. By integrating multiple approaches, scientists piece together the fine-scaled timeline of ice advances and retreats and the accompanying biological shifts. This multidimensional dating system underpins our understanding of Earth's complex glacial dynamics and even offers insights into ancient atmospheric composition and climate. Ice cores extracted from polar ice sheets and glaciers are remarkable climate archives. Each annual layer of snowfall compresses into a capsule of ice that traps tiny air bubbles, snapshots of the atmosphere at the time of deposition. Analyzing the gases within these bubbles, such as carbon dioxide and methane, reveals past climate fluctuations, highlighting periods of warming and cooling throughout the last several 100,000 years. High concentrations of greenhouse gases usually point to warm interglacials, while low levels mark glacial periods. Ice cores, however, hold many other climate clues. Layers capture volcanic ash and dust that record eruptions or shifts in atmospheric circulation. Isotopic analysis, especially oxygen-18 and deuterium, reveals ancient temperatures because lighter isotopes evaporate more in warm times, leaving distinctive signatures. The layered structure lets scientists build detailed chronologies, counting annual bands much like tree rings to pinpoint dates. By matching these climate shifts with other paleoecological data, researchers deepen their understanding of Earth's climate system, refining links between atmospheric composition, temperature, and orbital factors. Reading these multi-layered records provides vital insight into natural climate variability and possible future trends. The precise information from ice cores underpins broad studies of Earth's dynamic climate history, tying past, present, and future into a single narrative. To reconstruct ancient ice movement, scientists combine careful fieldwork, modern visualization, and geochronological methods.
Glacial features, striations, crevasse patterns, moraines, drumlins, and outwash plains reveal the direction, speed, and extent of past ice sheets. High-resolution aerial photography, satellite imagery, and LiDAR surveys have dramatically improved mapping of these forms across vast, hard-to-reach terrains, delivering detailed topography that uncovers subtle relief otherwise missed. Merging visual data with ground investigations yields a comprehensive spatial analysis that distinguishes glacial landforms from those created by other processes. Optically stimulated luminescence, radiocarbon, and cosmogenic nuclide dating, such as beryllium-10 and aluminium-26, allow scientists to determine when specific surfaces were exposed, establishing the timing of glacier advances and retreats. These age markers build a chronology of ice sheet movements and link landscape changes to climate records. Additional evidence comes from sediments deposited in glacial lakes and marine basins. Cores from these deposits contain pollen, microfossils, and chemical traces that help reconstruct environmental conditions throughout different phases of glacial periods. By integrating landform analysis, geochronology, and sediment studies, researchers create detailed reconstructions of ancient ice dynamics, showing how glaciers behaved, how they responded to climate shifts, and what controls drive glacial cycles. Climate models remain indispensable tools for exploring these conditions and their cyclic nature.
Complex climate simulations bring together countless variables: orbital parameters, atmospheric composition, ocean currents, and land surface properties to recreate the world of ancient ice ages. By feeding geological chronicles, ice core records, and sediment data into dynamic models, researchers generate temperature, precipitation, and ice sheet extent curves that span thousands of years. The models rest on physical and climatological laws that translate astronomical cycles, like those described by Milankovitch, into measurable impact on Earth's climate system. For example, shifts in axial tilt and orbital eccentricity redistribute solar energy, and the simulations reproduce the resulting climate swings. Feedback mechanisms are also built in. Changing ice sheet albedo, variations in greenhouse gas concentrations, and other interactions weave a coherent picture of climate evolution. The power of these models lies in their ability to test past time hypotheses across many scenarios with different starting conditions. They pinpoint the main drivers of glacial interglacial cycles and reveal how volcanic aerosols, oceanic heat transport, and related factors amplify or dampen climatic signals. Regional differences emerge too, why some areas endured severe glaciation while others stayed relatively mild, helping to interpret local geological and paleontological evidence. The process, however, is extremely demanding. Model accuracy hinges on the quality and resolution of input data, which often carry uncertainties. Fully reproducing Earth's climate, especially the ocean-atmosphere coupling, requires massive computational power. Models keep improving, yet they evolve continuously as scientists strive to capture intricate feedbacks and the long timescales of ice age cycles. Ongoing refinements bring us closer to understanding deep-time climate and forecasting future dynamics. Reconstructing ancient glacial environments is like solving a complex puzzle hampered by the scarcity and fragility of surviving clues. Incomplete or disturbed geological records pose a major obstacle. Erosion, sediment buildup, and tectonic shifts can erase or distort key evidence, leaving gaps in the timeline. Precise dating adds another layer of difficulty. Radiocarbon methods revolutionized the field, but struggle with older samples, often yielding broad age ranges that blur detailed climate reconstructions. The preservation of organic remains depends on acidity, moisture, and temperature, which can either safeguard material or destroy it rapidly.
Because climate changes unevenly across the planet, regional variations in temperature, precipitation, and ocean currents created diverse habitats and climate regimes. Consequently, researchers must weave together data from many sites, each preserving its own fragment of the ancient climate story. During the later stages of the ice ages, it becomes especially hard to separate natural climate swings from human impact, which complicates environmental interpretation. Indirect proxies, such as the isotopic makeup of ice cores or sediment layers, add further uncertainty because many factors affect them, making precise reconstruction a challenging task. Overcoming these obstacles demands a truly interdisciplinary effort that links climatology, chemistry, biology, and cutting-edge technology. Modern advances have transformed our view of the glacial world. Satellite images and airborne LiDAR now map the edges, flow routes, and surface features of massive ice sheets with high-resolution detail, revealing subtle changes that once went unnoticed over decades or centuries. Improved radiometric techniques, including uranium series dating and optically stimulated luminescence, sharpen the timeline of glacial events and climate fluctuations, allowing us to match geological and biological responses more confidently. Deep drilling into Greenland and Antarctica yields ice cores that record atmospheric composition, temperature, and greenhouse gas concentrations for hundreds of thousands of years. Isotope analysis of these cores links carbon dioxide and methane swings to climate shifts and to external drivers such as solar insolation. High-performance supercomputers now simulate ice sheet dynamics together with ocean currents, atmospheric circulation, and feedback mechanisms, testing hypotheses about the causes of glacial cycles and projecting future changes. These computational models integrate diverse field data into a unified, quantitative framework, turning glacial research into a precise science that reconstructs ancient environments, clarifies the processes that shaped Earth's icy landscapes, and improves forecasts of coming climate trends.
A comprehensive understanding of the Ice Age complexity therefore relies on a collaborative approach. Climatology provides the basis for global temperature and orbital variations, while paleoclimatology, through ice core and sediment records, details past atmospheric composition, temperature, and even volcanic activity that influenced the system. Geology and geomorphology reveal how glaciers have carved valleys, shaped mountains, and left deposits over millennia. These changes record the dynamics of ice sheets and influence today's sea level and coastline outlines. Glaciology studies the mechanics of ice, its movement, buildup, and retreat, applying physical laws to explain growth and shrinkage. Biological sciences, especially paleoecology and evolutionary biology, trace how plants and animals responded to dramatic climate shifts. By examining fossil records, pollen layers, and DNA trapped in sediments, researchers reconstruct ancient ecosystems and migration routes. Archaeology adds the human dimension, showing how people adapted and survived in changing environments. New technologies have deepened interdisciplinary collaboration. Remote sensing and increasingly accurate computer models recreate past climates and ice behavior. Integrated models combine geological, climatic, and biological data, allowing scientists to test hypotheses about ancient environmental changes and their impact on ecosystems. As research advances, linking these scientific perspectives becomes ever more crucial. Each field contributes a piece of the puzzle, building a comprehensive picture of the complex dynamics of the Ice Age era. This joint approach not only sharpens our grasp of past climate variability, but also improves forecasts of future climate and its effects on modern ecosystems. The emergence of ancient DNA analysis has revolutionized our understanding of glacial ecosystems. offering a molecular window into the past that complements traditional fossil and sediment data. Unlike morphological remains, which reveal little about species diversity and population dynamics, ancient DNA precisely tracks genetic lineages, migrations, and adaptive strategies. Sequencing genomes from well-preserved specimens, bones from permafrost or frozen tissue, allows researchers to reconstruct whole population histories, detect interspecies hybridization, and uncover genetic adaptations to cold. Studies of woolly mammoths and extinct horses, for example, show how populations expanded, contracted, or hybridized as climates changed. Genetic evidence explains how species endured shifting conditions, often retreating to refugia or developing new traits, highlighting both the resilience and vulnerability of Ice Age communities. Ancient DNA also clarifies predator-prey relationships, revealing how their numbers rose and fell together, and how ecological balances reshaped over thousands of years. It helps pinpoint the timing and causes of extinctions and untangles the interplay between climate and human activity. Molecular data can refine models of how modern species respond to environmental pressures, showing the genetic capacity for adaptation in organisms that survived the Ice Age. In essence, ancient DNA has turned the story of glacial ecosystems from a static record of physical remnants into a dynamic narrative woven from genetic threads. It lets us peer into the evolutionary forces that shaped life across cold landscapes, revealing both the variety of past ecosystems and the survival tricks they used as the climate kept shifting. As ancient DNA research deepens, we're seeing clearer links between those old communities and today's biodiversity, helping us grasp how nature reacts to change. Glacial remnants continue to sculpt Earth's terrain long after the ice melted. The massive sheets carved valleys, fjords, and basins, leaving a relief that still steers regional climate and the places where species live. When the weight of the ice lifted, the crust rebounded, a process called isostatic rebound, raising former depressions into highlands and rerouting drainage. That reshaped the spread of fresh water, fertile soils, and natural barriers, directly influencing modern ecosystems and human settlements. Features such as moraines, drumlins, and eskers now host unique plant and animal communities, specially adapted to those microhabitats. Nutrient-rich glacial deposits sustain diverse flora and fauna, and in many places, the resulting fertile soils underpin agriculture, showing how ancient ice still feeds human activity. Meltwater from lingering ice feeds rivers and lakes, preserving ecological connections, supporting biodiversity, guiding fish migrations, and supplying water to nearby communities. The sheer size of past ice sheets and the flow of meltwater also affect ocean currents and atmospheric circulation, tweaking regional and global climate patterns. In this way, the legacy of the glaciers remains woven into the climate system that determines today's and tomorrow's environmental stability. Studying these icy leftovers highlights the resilience and adaptability of ecosystems. Knowing how landscapes transformed in the past helps us evaluate their present importance and steer the management of natural changes. Recognizing the deep imprint of ancient ice sharpens our view of Earth's dynamics, offering vital lessons as we confront modern climate challenges. Past glacial ages remind us that the climate system is mobile and can change abruptly. Research into frozen epochs uncovers the mechanisms behind climate variability and the tenacity of life in extreme conditions. A core takeaway is the fragile balance between greenhouse gases and global temperature. During glaciations, swings in carbon dioxide and methane drove the start and end of ice ages. Today, understanding those feedback loops stresses the need to watch emissions closely. Tiny shifts can spark major climate swings. The history of ice sheet growth and retreat also shows how ocean currents and continental positions deeply influence climate, with past circulation changes reshaping heat distribution, regional climates, and sea levels. These insights highlight why healthy oceans matter and why we must curb human-driven pollution, overfishing, and other disturbances that threaten climate stability. They also teach us about the resilience and adaptability of ecosystems and species. Ancient extinction events and migrations show how life can innovate or falter when environments shift rapidly. Understanding those patterns guides modern conservation, underscoring the need to protect genetic diversity and migration corridors as the climate changes. Archaeological finds of past technologies, migration tactics, and social organization reveal human ingenuity in the face of hardship. That legacy urges today's societies to adopt sustainable practices and flexible policies that can shield us from future climate shocks. Grasping ancient climate biological cycles exposes the tight link between Earth's climate system and living responses, encouraging a proactive stance, scientific vigilance, adaptive management, and global cooperation to temper current and forthcoming changes. Modern permafrost, frozen soil, rock, and organic matter that remains at or below freezing year-round, is a relic of the last glacial age. Vast ice sheets once covered much of the northern hemisphere, their weight reshaping the land, cooling the surface, and carving valleys and fjords that persist today. During glacial maxima, the cold drove permafrost deep inland, trapping plant and animal remains that now offer priceless clues about past ecosystems, climate swings, and even animal migrations. When the last ice age ended, warming caused glaciers to retreat and parts of the permafrost to melt, releasing stored methane and carbon dioxide and influencing subsequent climate variability. Today's permafrost zones act as living archives of those glacial conditions. Their extent and stability reflect the balance between present climate and ancient ice age legacies. Thawing permafrost threatens global climate because the liberated greenhouse gases can accelerate warming, while in high-latitude regions, residual cold still preserves permafrost, mirroring past conditions. Frozen ground continues to shape ecosystems, affect construction, and serve as a key indicator of how Earth's climate system responds, directly tying our present to a distant, icy past. Glacial cycles remain one of the chief drivers of long-term climate change, sculpting the planet's natural mosaic over tens to hundreds of thousands of years. Glacial cycles are driven mainly by modest shifts in Earth's orbit, its eccentricity, axial tilt, and precession. These changes alter how much solar energy reaches different parts of the planet, producing long periods of cooling and warming that go far beyond individual ice ages. When eccentricity and tilt increase, polar regions receive less sunlight in winter, allowing ice sheets and glaciers to expand. Conversely, when the orbital configuration directs more direct sunlight toward the poles, the ice retreats and warm interglacial periods begin. These orbital swings reshape not only the area and thickness of ice, but also broader climate patterns. Atmospheric circulation, precipitation regimes, and ocean currents all adjust. By redistributing global heat, they influence climate stability over millennia. The combined effect of the cycles shows up as long-term fluctuations that control how often, how long, and how intense glacial periods are. Such fluctuations have repeatedly raised and lowered sea level by hundreds of meters, flooding and exposing continental shelves,
opening and closing migration routes, and altering ocean pathways that help regulate climate. The interplay of orbital mechanics and climate feedbacks works like a planetary thermostat, governing Earth's long-term climate variability. Understanding these cycles reveals how celestial motions are tightly linked to Earth's climate system and underscores the profound impact of cosmic rhythms on the planet's history. This perspective is essential for judging today's climate changes and their possible long-term effects. The legacy of the last ice age still shapes human settlement and infrastructure. Deep valleys, fertile moraines, and broad plains carved by ice provide both opportunities and challenges for modern communities. Glacial valleys often form natural transport corridors, guiding the growth of towns across rugged terrain. Mineral-rich soils left by glaciers support agriculture and dense populations in some regions. At the same time, these glacial landforms pose hazards. Ancient deposits can weaken foundations, and permafrost, common in former glacial landscapes, requires special engineering to prevent subsidence and structural damage. As temperatures rise, thawing ground can collapse, harming roads, pipelines, and buildings, highlighting the delicate balance between using glacial heritage and managing its risks. Remaining glacial features also affect water management. Moraines and drumlin fields act as natural aquifers, storing fresh water, yet their uneven terrain can impede drainage and increase flood vulnerability. Ice deposits left by past glaciers along the coast are now feeling the effects of rising seas, which complicates city planning and threatens the stability of shoreline infrastructure. Planners already take the legacy of former ice ages into account when they assess hazards and shape land use policies. Mapping zones that could experience glacial lake outburst floods or landslides in glacial sediments helps societies lower those risks. As humanity adjusts to a more variable climate, grasping how glacier-formed landscapes influence the land becomes increasingly vital. It guides smarter use of terrain, the construction of resilient infrastructure, and the preservation of natural features that have shaped human life for millennia. Yet rapid global warming raises serious doubts about the survival of this glacial heritage. Ancient ice sheets, permafrost layers, and other glacier-created forms act as priceless archives of Earth's climate past. They record natural variability and can reveal how the planet responded to earlier changes.
However, rising temperatures destabilize the delicate balance that keeps these archives intact. When residual ice sheets melt, landforms that have existed for thousands of years may disappear, erasing a critical geological record and hindering our ability to reconstruct past climates. Permafrost is especially vulnerable. It often stores organic material from previous ice ages, and thawing can release huge amounts of methane and carbon dioxide, further accelerating warming. These feedback loops not only speed up climate change, but also blur the original climate signals trapped in frozen layers, making future modeling more difficult. The breakdown of permafrost also leads to ground subsidence, reshaping landscapes and ecosystems that have remained stable since the last glaciation. This reshaping threatens both natural habitats and human settlements. Moreover, the loss of glacier-formed features adds uncertainty to sea level rise projections. Melting remnants contribute water in ways that are hard to predict, especially when feedbacks hasten ice loss. The resulting impacts could mirror or even exceed the dramatic changes that marked the end of previous ice ages, but they are occurring far more quickly. Destruction of glacial heritage complicates the interpretation of paleo-environmental data, making it harder to separate natural climate fluctuations from those driven by humans. Understanding how these forms fare in a warming world is essential for safeguarding Earth's geological record and for refining climate forecasts. Preserving these natural archives enables scientists to anticipate how today's shifts will reshape the planet over the coming century, and underscores the need to weave past climate responses into modern predictions. Research on past glaciations supplies invaluable information that sharpens the accuracy and reliability of climate models. By studying sediment layers, ice cores, and the landforms left by ancient glaciers, researchers obtain detailed chronicles of former climate variability. Ice cores, in particular, act as time capsules that trap carbon dioxide and methane, allowing precise reconstruction of ancient greenhouse gas concentrations and giving us a clearer picture of Earth's climate history. Historical climate records reveal how Earth's climate system has responded to various forces, orbital shifts, volcanic eruptions, and others, and identify the thresholds that triggered moves between glacial and interglacial periods. The behavior of ancient ice sheets informs models about feedback loops and nonlinear reactions. Knowing how ice growth and retreat alter sea level and surface reflectivity sharpens predictions of future sea level rise under different emission scenarios. Investigating glacial erosion and accumulation refines surface process and sediment transport models, tying simulations to real thousand-year climate fluctuations. This historical context improves model sensitivity to forcings, making forecasts more reliable and deepening our grasp of the timing and scale of upcoming climate shifts. As models advance, they increasingly capture the intricate interplay of atmosphere, ocean, and land, turning the study of past glacial ages into a foundation for anticipating and managing future challenges. Glacial age deposits, sediments, moraines, and related materials are priceless archives of Earth's geological and natural history. They preserve details of ancient climates, vegetation, and mineral distributions, guiding geologists to rich deposits of rutile, coal, hydrocarbons, and other resources that often accumulate in glacial landscapes. Ice-driven erosion and buildup frequently concentrate valuable minerals, creating promising exploration targets. Beyond minerals, these deposits host porous layers formed by meltwater channels and moraine plains, which serve as significant aquifers. Mapping their stratigraphy defines groundwater boundaries and helps assess the sustainability of water extraction, especially where modern supplies rely on ancient deposits. The varying fertility and stability of moraine-covered soils influence agriculture and construction, informing land use planning and preventing subsidence or erosion. In coastal regions, remnants of glacial deposits are factored into sea level rise projections, shoreline shift forecasts, and mitigation strategies. Analyzing the preserved ancient conditions also enhances understanding of ecosystem responses to climate change, supporting biodiversity conservation as the planet warms. In short, glacial deposits are dynamic records that shape our knowledge of natural resources, environmental resilience, and responsible management in a changing world. Delving deeper into ancient layers reveals the data we need for future research and new possibilities. Discoveries of Ice Age fossils and artifacts have dramatically broadened our picture of life in that frigid world. Among the most striking finds are the massive bones of megafauna, mammoths, mastodons, saber-toothed cats, and other giants. These remains not only detail animal anatomy and adaptations, but also illuminate each species' ecological role. Exceptionally preserved Siberian mammoth specimens, for example, have disclosed diet, migration routes, illnesses, and injuries, painting a vivid portrait of survival under harsh conditions. Cave paintings, such as those at Lascaux, give us a glimpse into the cultural life of Ice Age peoples. Their intricate depictions of hunts and horses reveal both the importance of hunting and the spiritual symbolism that permeated early societies. Associated artifacts highlight the complex relationship between humans and their environment, showing emerging art, ritual practice, and symbolic thought. The limestone figurines of the Venus of Willendorf, with their finely crafted features, suggest ceremonies linked to fertility, survival, or spiritual belief, offering insights into the world-view of their creators. More recent excavations of Altamira and Chauvet have uncovered wall paintings over 30,000 years old, combining animal images with abstract signs and marking a clear evolution of thought and culture. Each discovery deepens our understanding of the Ice Age flora and fauna, while showcasing human ingenuity in a demanding world. Among the most informative sites is the La Brea tar pit in Los Angeles. Unlike typical sedimentary fossil beds, the natural asphalt trap preserved an extraordinary cross-section of Pleistocene megafauna and smaller creatures. Sticky tar rose to the surface, ensnaring animals that could not escape, resulting in a dense collection of bones, many still bearing soft tissue traces, meticulously excavated and studied. The La Brea assemblage extends knowledge far beyond skeletons. It includes everything from mammoths and mastodons to wolves, saber-toothed cats, and giant ground sloths, vividly illustrating predator-prey dynamics. From these remains, scientists have reconstructed food webs, migration patterns, territorial behavior, and adaptations to shifting climate and resource availability. The preservation of juveniles and injured individuals provides clues about the challenges of survival and the impact of natural stresses. Stratigraphic context has allowed researchers to date the timing and pace of Ice Age extinctions. Many species represented in the pits vanished shortly after the last glacial maximum, pointing to climate change and human activity as primary drivers. Tools and other signs of human interaction found in the same layers deepen our understanding of early hunting techniques and adaptive strategies. Thus, the Brea is more than a paleontological curiosity. It opens a window onto the fragile balance of Ice Age ecosystems and helps explain why megafauna communities flourished and then declined. New discoveries keep sharpening climate models, extinction patterns, and human-environment links, showing how much the frozen record still offers scientists. Mammoth fossils are a turning point for Ice Age research, providing priceless clues about landscape, ecosystems, and how people lived in the cold world. Permafrost often preserves bones, hair, and stomach contents, letting researchers reconstruct the animal's appearance, diet, health, and behavior, and map the food webs that supported the megafauna. These data deepen our view of the ecological networks that sustained the giants and the climate they required. These remains also reveal adaptation strategies. Thick coats, fat layers, and special leg bones are direct responses to relentless cold, illustrating the selective pressures of glacial terrain. The same evidence helps explain why most mammoth groups disappeared at the Ice Age's end, when climate change and human hunting combined. Human sites near mammoth remains frequently contain tools, weapons, and carvings, highlighting the giants' central role in survival. The bones let us trace hunting methods, scavenging, possible early domestication, and how people turned mammoth parts into food, clothing, and cultural symbols. Thus, the fossils act as time capsules linking climate, ecology, and human ingenuity. Cave art offers another vivid window. Wall images capture daily life, spiritual ideas, and social bonds of Ice Age peoples. Detailed depictions of mammoths, bison, and reindeer show these animals were both resources and symbols. The choice of scenes, perspective, and recurring motifs reveal sophisticated thinking, abstract concepts, and shared cultural rules. Analyzing the style and placement of the drawings uncovers the cognitive abilities of these people, including abstract thought and communal rituals that guided hunts and strengthened community ties. Repeated motifs and patterns in ancient art may be some of the earliest attempts to record stories or pass on collective memory, linking generations. In many caves, red ochre markings and intentional carvings point to ritual or spiritual use of the space. Embedding artwork in the natural landscape reflects a worldview in which people felt a kinship with depicted animals and spirits, turning art into a cultural chronicle that complements tools and shelters. Large Ice Age sites, European caves, Siberian shelters, lakeside camps preserve tools, bones, dwellings, and paintings, offering a vivid glimpse into a frozen world. Their excellent preservation lets scientists reconstruct climate, vegetation, and animal communities across different glacial phases. Radiocarbon and other dating methods provide precise chronological anchors, aligning environmental shifts with human adaptations. Mammoth remains found alongside sophisticated tools demonstrate both the presence of megafauna and the ingenuity of people who exploited available resources. Cave imagery records now-vanished flora and fauna, enriching paleo-ecological knowledge. The Denisova cave in Siberia yielded ancient DNA that mapped migration routes and interbreeding events, reshaping our view of human evolution. Sediment layers and pollen analyses reveal temperature swings, rainfall patterns, and plant zones throughout glacial periods. As technology advances, high-precision radiocarbon dating, ice core scanning, genome sequencing, archaeological sites become interdisciplinary laboratories where archaeology, paleontology, geology, and genetics intersect. They serve not only as windows into the past, but also as keys to understanding how climate change, ecological shifts, and human creativity together forged the legacy of the Ice Age landscape. And ongoing excavations promise to deepen that insight. Advanced dating techniques have dramatically sharpened the precision with which we can place artifacts, fossils, and sediment layers in time, allowing researchers to trace migration routes and climate shifts with unprecedented clarity. By extracting and analyzing ancient DNA from both humans and megafauna, scientists have uncovered intricate interspecies relationships, migration pathways, and adaptive strategies that helped populations survive the oscillations of Ice Age climates. LiDAR, initially developed for topographic mapping and military purposes, has become a key tool for revealing subtle landscape features hidden beneath vegetation or ice sheets. Detailed three-dimensional maps of formerly unknown archaeological sites now expose previously overlooked settlements, tool complexes, and migration corridors. These discoveries have identified early occupation zones in regions once thought uninhabitable, expanding our view of human resilience and flexibility. Multispectral satellite remote sensing further extends our reach, enabling large-scale investigations of deposits, relief, and the advanced retreat patterns of glaciers over millennia. At the same time, sophisticated computer models that weave together climate records, ocean currents, and geological chronologies simulate ancient scenarios and forecast glacial responses to various forces. Such simulations help resolve long-standing disputes about the timing and mechanisms of rapid glacial expansions and contractions, deepening our understanding of ice sheet stability. Genomic technologies have also been pivotal in revealing the genetic diversity and migration histories of both cold-adapted species and early humans. Sequencing well-preserved ancient remains illustrates how populations adapted to sudden declines and highlights interspecies connections. These insights have reshaped the timeline of human dispersal and megafaunal extinctions, underscoring the dynamic interplay between climate and biological response. The continual fusion of technical advances keeps challenging entrenched ideas and spawning fresh hypotheses, promising ever more detailed reconstructions of the Ice Age world. Debates persist, especially regarding the exact chronology of glacial advances and retreats. Radiocarbon dating and ice core analyses provide important temporal markers, yet methodological discrepancies and gaps in the fossil record fuel uncertainty about whether glacial fluctuations occurred synchronously worldwide. This controversy influences reconstructions of climate change rates, regional differences, and the broader models of Earth's climatic history. Another ongoing contention concerns the drivers behind the abrupt climate shifts of the late Pleistocene. Some researchers argue that massive influxes of fresh water disrupting oceanic currents were the primary trigger, while others point to amplified responses to orbital variations or heightened volcanic activity. The divergence stems from differing interpretations of sedimentary and ice core proxies, each side emphasizing distinct mechanisms for the rapid changes observed. These scholarly disagreements extend beyond academia, shaping our grasp of modern climate resilience and the potential for sudden environmental shifts. Persistent investigations of fossil evidence continue to illuminate the patterns of megafaunal disappearances, refining our comprehension of past extinctions and informing present-day climate perspectives. Climate certainly mattered, yet the extent of human hunting and habitat alteration remains debated. Different arrival times of people in various regions blur the picture, sparking arguments about cause versus coincidence. This drives the need to weave many lines of evidence into a nuanced view of natural variability and human impact. The very debates highlight how fluid paleoclimatology is and why ongoing research is essential. As scientists refine methods and retest assumptions, they deepen our grasp of Earth's climatic past, reminding us that even well-accepted findings can be reshaped by new data. Accurate dating of ancient sediments, ice cores, and fossils lets researchers reconstruct detailed climate swings over hundreds of thousands of years. The records reveal regular patterns of temperature, atmospheric composition, and ocean changes, linking orbital cycles, greenhouse gases, and major climate shifts. Exceptionally preserved plants and animals directly show ecosystem reactions. Shifts in ranges, migration timing, and extinctions outline climate tolerance limits and the speed of ecological adaptation. These insights sharpen models of how climate variability affects biological resilience and provide valuable predictions for today's warming world. Studying glacial deposits and landforms also uncovers the size and movement speed of ice sheets, improving our understanding of ice dynamics under different climate scenarios. Better sea level reconstructions emerge, showing how glacial cycles reshaped coastlines and global geography, knowledge that is critical for assessing current sea level rise and coastal vulnerability. Interdisciplinary work that blends climate modeling, geology, paleobotany, and archaeology further clarifies how climate shaped human evolution, migration wards, and cultural development. As research advances, scientists continually reveal new layers of Earth's climate complexity, enriching past understanding and enhancing the predictive models needed to meet present and future climate challenges. The difficulty of pinpointing when climate shifts began and ended, especially the start and finish of glacial periods, poses a major challenge for scientists. Ice cores from Greenland and Antarctica hold priceless clues about past atmospheric composition and temperature, yet they represent only a fragment of the global picture. To fill the gaps, researchers must weave together many indirect records: marine sediments, land deposits, cave formations, each with its own limitations and dating uncertainties. This melding demands sophisticated models that can turn diverse datasets into coherent climate reconstructions. The very dynamics of ice sheets add another layer of complexity. Modern models strive to mimic how ice responds to warming, but accurately capturing basal sliding, iceberg carving, and subglacial hydrology remains elusive. These processes are crucial because they dictate ice stability and directly influence forecasts of future sea level rise. Incorporating feedbacks such as albedo changes and ice-climate interactions further thickens the modeling task. Linking glacial cycles to the biosphere and human societies pushes the challenge even farther. Paleoclimate evidence must be combined with archaeology, genetics, and ecology to reveal how ancient populations reacted to climatic variability. Merging these disciplines and translating past patterns into future predictions sits at the cutting edge of climate science. Advances in technology, particularly artificial intelligence and machine learning, promise a breakthrough. AI excels at uncovering faint patterns hidden within massive data troves that conventional statistics often miss. By integrating ice core information, sediment layers, and fossil distributions, machine learning algorithms produce more precise timelines of climatic oscillations. They identify cycles and drivers, orbital variations, greenhouse gas concentrations, oceanic shifts, and clarify how these forces trigger the advance or retreat of ice. Simulations powered by AI can simultaneously handle countless variables, allowing researchers to test diverse hypotheses about ice sheet behavior under varied boundary conditions. They reveal how small tweaks in Earth's orbit or atmospheric makeup can push the climate past thresholds between glacial and interglacial states. As new drilling results, satellite observations, and climate indicators flow in, machine learning systems continuously refine forecasts, deepening our confidence in them. Neural networks also analyze ancient biological and geological records, exposing how ecosystems and landscapes responded to climate change. This insight helps identify feedback loops that amplified or dampened past climate events and improves models of future climate resilience. Moreover, AI can pinpoint regional differences in ice sheet dynamics, showing how local factors contribute to global patterns. Artificial intelligence and machine learning are now letting scientists date key glacial events, rapid melt-offs, and sudden climate swings with unprecedented precision. A tighter timeline lets researchers line up those climate milestones with external drivers, such as volcanic eruptions and solar variability, sharpening our picture of what happened in the past and improving forecasts for a warming world. By dissecting the timing, length, and speed of past ice age transitions, researchers pinpoint thresholds and tipping points that foreshadow abrupt future changes. The ancient record shows how ice volume, greenhouse gas concentrations, and ocean circulation responded together to shifting conditions, giving models a realistic basis for non-linear behavior. Ice cores and sediment layers are especially valuable, preserving ancient atmospheric composition and offering benchmarks to test climate simulations. Understanding how temperature and greenhouse gas levels moved in lockstep during earlier cycles helps calibrate model sensitivity to subtle atmospheric tweaks. Detailed chronologies of ice advances and retreats also refine predictions of how today's ice sheets might react, potentially disintegrating non-linearly and raising sea levels dramatically. Paleoecological evidence of changing flora, fauna, and human societies underscores the importance of ecological resilience and adaptation, feeding back into models that capture climate-biosphere interactions, including carbon cycle dynamics. Rapid fluctuations recorded in events like the Dansgaard-Oeschger episodes demonstrate that the climate system can shift swiftly, far faster than linear projections would suggest. This insight pushes model developers to incorporate mechanisms for sudden, large-scale transitions. As computational power grows, simulations can resolve finer processes such as cloud formation, ocean eddies, and permafrost feedbacks, which often amplify or dampen broader climate signals. Integrating dynamic ice sheet modules into comprehensive climate frameworks deepens our grasp of how ice mass loss contributes to sea level rise and regional climate shifts, yielding a more complete Earth system picture. Continuous refinements, anchored in detailed paleoclimatic reconstructions and bolstered by ever greater computing resources, are essential for producing reliable future forecasts and helping societies prepare for impacts rooted deep in Earth's climate history. Research on Earth's biogeochemical cycles, especially carbon and nitrogen, has produced models that capture millennial-scale effects of biological productivity and human activity on atmospheric composition. Integrating these processes lets scientists forecast how future emissions and land use changes will interact with natural climate variability. International collaborations that build shared climate archives and run joint computational experiments have sharpened model testing, allowing researchers worldwide to run scenarios and boost reliability. The deeper our grasp of Earth's feedback loops, the more precisely models can reproduce the fragile balance of long-term change. This demands close cooperation among climatologists, geologists, ecologists, and policy experts, ensuring models stay anchored in empirical data and improving predictions of future climate dynamics. Global teamwork also drives ice age and climate science. The complexity of glacial phenomena, from ice dynamics to paleoclimate reconstructions, requires diverse expertise and data exchange that no single nation can provide. Joint projects pool resources for deep core drilling, high-resolution mapping of ancient landscapes, and the construction of global models. In European Antarctic drilling initiatives and international ocean research programs, scientists coordinate data collection and analysis to build a coherent picture of climate fluctuations over millions of years. Partnerships standardize methods, making results comparable across regions and disciplines. Merging archaeological, geological, and climatic data from many countries refines reconstructions, revealing human migrations, volcanic events, and environmental shifts of the last ice age. International networks accelerate the spread of discoveries, foster global dialogue, and spark innovation. They often include training programs that build scientific capacity in less wealthy nations, expanding research horizons and introducing varied perspectives. These collaborations are vital for today's climate challenges. Lessons from ancient variability guide future forecasts. Beyond research, they nurture a shared sense of responsibility for Earth's history and environment. By working together, scientists, policymakers, and educators lay the groundwork for solutions that balance scientific insight with societal needs. Public awareness of glacial dynamics, past climate swings, and the delicate equilibrium of permafrost and ice sheets empowers people to become active participants in sustainable decision-making, underscoring the need to protect vulnerable regions for generations to come. Understanding how glaciers and permafrost regulate Earth's climate can foster a sense of responsibility. When people learn that thawing permafrost releases methane and other trapped gases, they recognize feedback loops that can accelerate warming. This knowledge often leads to stronger support for emission reduction policies, habitat protection, and funding for research. It also dispels myths and encourages thoughtful debate about geoengineering and resource extraction in icy regions. Effective scientific communication equips residents of ice-rich landscapes with tools for sustainable land use, resilient infrastructure, and adaptive strategies. In areas vulnerable to permafrost melt, education promotes practices that reduce environmental damage and safeguard structures. Citizen science projects, such as monitoring glacier retreat or permafrost temperature, provide valuable data and reinforce collective accountability. An informed public influences policymakers, who frequently need popular backing to enact climate-friendly legislation. When societies are scientifically literate about glacial history, governments are more likely to prioritize climate resilience, nature conservation, and international cooperation to protect the Arctic. Rising global temperatures deepen the consequences for glaciers and permafrost. These frozen reservoirs are key indicators of climate stability. Their alteration threatens the planet's future. Warmer conditions speed up glacier melt worldwide, raising sea levels enough to reshape coastlines and displace communities. The loss of glaciers also curtails fresh water supplies for millions, affecting agriculture, drinking water, and ecosystems that depend on seasonal runoff. In polar and subpolar regions, permafrost thaw releases large stores of organic carbon. As microbes decompose this material, they emit methane and carbon dioxide, potent greenhouse gases that further heat the climate. This positive feedback can intensify global warming and complicate climate scenario forecasting. Thawing ground loses stability, leading to erosion, infrastructure damage, and challenges for indigenous peoples and local economies. Ecologically, retreating ice shrinks or shifts habitats for specialized plants and animals, endangering biodiversity and altering community dynamics. Newly exposed terrain may erode quickly and invite invasive species that disrupt existing ecosystems. Moreover, disappearing reflective ice exposes darker land and water, enhancing heat absorption and amplifying regional and global warming. Grasping these potential changes is essential for shaping adaptation plans. Remote sensing and climate models improve predictions of glacier melt rates and permafrost degradation, helping societies prepare for the evolving climate reality. These data steer political choices and underline the urgency of cutting greenhouse gas emissions to soften irreversible planetary shifts. As the record grows, grasping the intricate link between climate change and Earth's ice sheets becomes ever more critical. They act both as indicators and drivers of planetary health. Ongoing research and advancing technology are deepening our insight into past glacial periods and promise to reshape our view of Earth's climate history and its future trajectory. Improved paleoclimate markers, such as refined ice core analyses, sediment chronicles, and novel isotopic techniques, are tightening the timing and mechanisms of abrupt climate shifts. Discovering previously unknown episodes of volcanic or solar activity could clarify their role in triggering or ending glaciations, testing models that emphasize orbital variations and greenhouse gas feedbacks. New DNA analyses of ancient plants and animals may reveal unexpected resilience strategies and extinction patterns, showing how ecosystems responded to rapid climate swings and helping predict whether modern species can cope with ongoing change. Next-generation climate models that weave together atmospheric, oceanic, biospheric, and cryospheric interactions are set to deliver more accurate simulations of ancient climates. These models may uncover hidden feedbacks, the influence of subglacial lakes or permafrost dynamics that shaped past transitions, reshaping our understanding of the stability of today's ice sheets and the risk of swift melt.
Expanded drilling projects and remote sensing technologies are opening fresh sections of the geological record, exercising regional climate variability and complex, mosaic patterns of Earth's glaciations. In sum, forthcoming discoveries will untangle the tangled web of factors driving the planet's climate, offering vital lessons for policy, conservation, and our broader comprehension of Earth's dynamic systems.